Night after night, long before civilization built cities or wrote words on parchment, human beings looked up in wonder at the sky. In the darkness above untouched plains and forests, an endless tapestry of stars shone down. With no scientific instruments and no recorded formulas, those first sky watchers relied on their eyes, their stories, and a deep curiosity. They gathered around crackling campfires and pointed out patterns in the sparkling night. Under a sky unspoiled by any man-made light, the universe must have felt immense, yet intimately close. A dome of mystery arching over the little world of human concerns. In those prehistoric times, the sky served many purposes at once. It was a calendar, a clock, a guide, and a source of wonder. The slow dance of the sun, moon, and stars across the heavens told our ancestors when the seasons were turning, when the cold of winter would give way to spring's renewal. By watching the sunrises and sunsets, they learned to anticipate the longest day of summer and the longest night of winter. Each new moon and full moon marked the passage of time in a world without mechanical clocks. For people whose lives depended on the migrations of animals and the ripening of wild plants, these celestial patterns were essential knowledge, the difference between hunger and plenty. Beyond survival, the sky was a canvas for the human imagination. Every culture began to weave stories into the stars. They saw figures in the constellations, a great hunter chasing his prey across the night, a proud queen sitting among the heavens, a wandering hero immortalized in the stars. Tiny clusters of lights became legendary animals or ancestors watching from above. These myths gave meaning to the glittering points of light. To early humans, the sky was alive with deities and spirits. A bright star appearing at dusk might be a benevolent guardian. A comet streaking unexpectedly through the sky could be an omen from the gods. Each sunrise was a triumph of light over darkness, and each eclipse a moment of cosmic uncertainty that could send people to their knees in awe or fear. Imagine a clear, moonless night, tens of thousands of years ago. A small band of people gathers under a sky brimming with stars. Perhaps an elder lifts a hand and points to a familiar cluster, maybe what we call Orion's belt, 3 bright stars in a row, and begins to recount a story tied to that pattern. The others, young and old, listen closely, faces lit by firelight as much as by starlight. In that moment, storytelling and astronomy are one and the same. The stars become theatre for myth, and the act of observing them becomes a ritual passed from one generation to the next. Around that fire, under that vast sky, knowledge is not written in books, but etched in memories and shared in spoken tales. Over time, these observations grew more keen. People noticed that certain stars rose in the east at dawn only during particular seasons. For instance, much later in history, the Egyptians would note the star Sirius rising at sunrise, just before the Nile River flooded each year. A crucial piece of information for agriculture. Long before that, early hunter-gatherers surely learned that the appearance of specific stars, or the phase of the moon, could signal when herds migrated or fruits ripened. By paying close attention to the heavens, our distant ancestors found a reliable guide to life's rhythms on Earth. Here and there, evidence survives of this prehistoric astronomy. Deep in caves in France and Spain, alongside ancient paintings of bison and horses, there are dots and symbols that some researchers interpret as star maps or lunar calendars. A series of dots painted in the Lascaux cave, dating back 17,000 years, might represent the phases of the moon or even a constellation like the Pleiades cluster. In Germany, Archaeologists discovered a carved mammoth tusk over 30,000 years old, with patterns of notches that could correspond to the cycle of the moon or the stars in Orion. We cannot be certain that these are intentional sky records, but they tantalize us with the possibility that even in the last ice age, humans were charting the heavens in their art and artifacts. As generations passed, knowledge of the sky deepened and was passed down through oral tradition. Early humans moved from purely hunting and gathering towards settled life, and with that change, the sky's importance only grew. The moon's roughly 29-day cycle provided an easy way to count out the length of a month. Many early communities linked the moon's cycle to female fertility or to the planting of crops, reinforcing the idea that human life was connected to celestial rhythms. Rituals and ceremonies often aligned with celestial events. A tribe might hold a celebration on the night of the full moon, or a day of reflection at the winter solstice when the sun reached its lowest arc in the sky and the year's longest night arrived. For these ancient people, observing the sky was not just practical, it was often sacred. The earliest priests or shamans were likely skilled sky watchers. They studied the heavens for signs from the divine. A sudden new star, what we now know as a nova, flaring into view, or a lunar eclipse darkening a full moon, could send a ripple of alarm or wonder through a community. During a solar eclipse, when daylight mysteriously faded and the sun seemed to be swallowed by darkness, we can imagine the eerie silence that might fall over a gathering of people. Birds would hush, the air would cool, and a sense of dread or awe would grip everyone until the sun's light returned. To appease or understand such cosmic events, early societies developed rituals, perhaps banging drums or offering prayers when the sun was in eclipse, in hopes of bringing back the light. Through myth and ritual, early skywatchers laid the groundwork for astronomy without yet knowing the science behind it. By carefully observing the changing heavens, they learned to predict seasonal changes and celestial events in a rudimentary way. They might not have understood why the sun rose a little farther south or north each day throughout the year, but they knew it happened and marked those extremes. Many of their rituals, dances, feasts, or commemorations coincided with these celestial milestones, inscribing the sky's pattern onto their cultural calendars. In doing so, they preserved vital knowledge: the time to start a long migration, the best moment to begin harvesting and storing food, or the omen of an approaching winter. Under the same sky that arches over us tonight, those ancient observers noticed something peculiar too. A few star-like points of light that moved against the background of the fixed stars. These were the wanderers, the planets. To the unaided eye, Mercury, Venus, Mars, Jupiter, and Saturn looked like bright stars. But unlike the true stars, they changed position noticeably over weeks and months. Early skywatchers tracked these wanderers as well, weaving them into their myths as gods or spirits roaming the heavens. The wandering of Mars or Venus in the sky may have been associated with particular deities of war or love. Though they could not yet decipher the planet's complex paths, people's recognition that not all lights in the sky are the same was another step toward a more systematic curiosity about the cosmos. Thus, in the long ages before formal science, humanity's romance with the stars began. The night sky was a grand mystery, but through patience and imagination, patterns emerged and became familiar friends. People found comfort and meaning in those patterns. A certain star rising before dawn might herald cooling weather or the time of a ceremonial gathering. A cluster of stars overhead in autumn might remind them of loved ones lost, now believed to dwell in the heavens. By observing and remembering, the first astronomers, though they would not have called themselves that, slowly built a base of knowledge. It was fragile and interwoven with legend, yet it was real knowledge, born of careful attention. Millennia passed. Those first Skywatchers' descendants carried on their careful observations, and as human societies grew more complex, as we formed villages, then towns, then the first great civilizations, our ability to record and organize knowledge grew too. What began as a campfire story or a carved symbol became lists of celestial sightings, primitive calendars, and eventually deliberate alignments of structures with the sky. The earliest chapters of astronomy were written in the languages of myth and ritual, but the stage was set for a new chapter. As the Neolithic age gave way to the age of cities and agriculture, people were ready to transform star lore into structured knowledge. The first civilizations would soon begin mapping the heavens in earnest, marking the true beginning of astronomy as an organized endeavor. As human societies moved from nomadic life to settled villages and then to the first cities, their fascination with the sky did not diminish. It deepened. The scattered observations of earlier millennia began to accumulate, forming a body of knowledge that could be shared, preserved, and refined. Across the world, ancient peoples started to map the heavens with intent and ingenuity. They found regularity in the movements above and used those patterns to shape calendars, guide agriculture, and inspire their cosmologies. The heavens held clues to the timing of rains and harvests, of migrations and festivals. By recording the positions of the sun, moon, and stars, civilization found a kind of cosmic rhythm, a reassurance that the sky's patterns were reliable, even as human fortunes rose and fell. One striking example of early sky mapping still stands on England's Salisbury Plain, the great circle of stones at Stonehenge. Some 4,500 years ago, people raised this ring of giant stones and carefully aligned it with the movements of the sun. Each year, on the summer solstice, the longest day, the rising sun climbs exactly above the heel stone and casts its light through the heart of the circle. Even today, crowds gather at dawn on that day to witness the sun's first rays framed by Stonehenge's ancient pillars. To its builders, this was surely a moment of both practical and spiritual significance, a celebration of the year's turning point, when days would slowly begin to shorten. Stonehenge was more than a collection of rocks. It was part observatory, part temple. Its stones and openings marked the passage of time in a monumental way. We can imagine Neolithic people gathered among those stones in pre-dawn darkness, awaiting the sunrise on the longest day. When the sun finally broke the horizon, and that beam of sunlight pierced the monument, it would have confirmed that the cycle of seasons was continuing as expected. It was both a practical marker and a deeply symbolic event, offering a sense of order and connection between their world and the sky. Stonehenge was not alone. Throughout the ancient world, many cultures built structures aligned with celestial events. In Ireland, the Neolithic tomb of Newgrange, built around 3200 BC, was engineered so that at dawn on the winter solstice, a shaft of sunlight would travel down a long passage and illuminate its inner chamber, a triumphant symbol of light returning on the year's darkest day. In ancient Egypt, the pyramids at Giza were oriented almost perfectly north-south, and temples were constructed to align with the rising sun or certain stars, tying their earthly architecture to cosmic order. Farther afield, in what is now the Sahara Desert, an even older site at Nabta Playa, circa 5000 BC, featured stones arranged to mark where the sun rose at the summer solstice. These examples show that long before the written word, people around the globe took great care to observe the heavens and build what we might call the first observatories. By aligning stones or temples with the sun's path or the rhythm of the stars, they created permanent calendars in the landscape and sanctified their connection to the cosmos. While monoliths and temples captured the sun's seasonal dance, ancient scribes began to record the night sky's more intricate patterns. In Mesopotamia, the cradle of civilization between the Tigris and Euphrates rivers, astronomy became a scholarly pursuit as early as 1000 BCE, and even before. There, priests and court scholars watched the skies from the tops of ziggurats, the stepped temple towers of cities like Babylon. Night after night, they noted the rising and setting of stars and planets, and wrote these observations on clay tablets in cuneiform script. Some of the oldest star catalogues come from this region. The Babylonians, inheritors of Sumerian star lore, identified constellations and tracked planetary movements systematically. They divided the sky into regions, a tradition that eventually yielded the concept of the zodiac. 12 constellations along the sun's yearly path. By around 1200 BCE, a compendium of Babylonian astronomy, known today as the Muel Apian. Tablets listed dozens of stars and their motions through the seasons, essentially serving as an early handbook for sky watchers. From such records came remarkable predictive power. Babylonian astronomers, through centuries of observations, learned to anticipate certain celestial events. They could predict lunar eclipses by recognizing the repeating cycle in which they occur. They tracked the wandering planets, Mercury, Venus, Mars, Jupiter, and Saturn, noting how these wandering stars sometimes slowed, stopped, or even moved backward, retrograde, against the starry background. Using clever arithmetic schemes, Babylonian scholars developed methods to forecast these motions. For instance, they knew when bright Venus would reappear in the dawn sky after months of being invisible, or when Jupiter would return to a particular constellation. To the people of that time, these predictions were not just scientific curiosities. They were entwined with astrology and statecraft. Celestial events were seen as omens, so being able to predict them gave political and religious leaders a sense of control or forewarning about the future. Indeed, in Mesopotamia, astronomy and astrology were two sides of the same coin. The night sky was regarded as a kind of divine script, the gods communicating through celestial signs. Every eclipse of the sun or moon, every appearance of a comet or a rare alignment of planets was thought to foreshadow events on Earth. Mesopotamian scholars compiled extensive omen lists. For example, a tablet might record that, if an eclipse occurs in this month, a great king will die, tying sky events to earthly outcomes. While we remember those interpretations as superstition, the effect on astronomy was to motivate extremely careful observation and record keeping. In trying to read the will of the gods in the sky, these ancient observers inadvertently laid down a foundation of rigorous data. Their clay tablets, baked hard and preserved, contained detailed reports of planetary positions and star appearances over centuries. In hindsight, they were doing science, even if their intent was to serve theology and royal interests. Ancient astronomy blossomed in other parts of the world as well. In China, court astronomers, by at least 700 BCE, and likely much earlier, were recording eclipses and the passage of comets, considering these events to be omens that could legitimize or threaten an emperor's reign. The Chinese developed their own star maps and identified dozens of constellations different from those of Mesopotamia or Greece. They tracked planetary motions and even noted unexpected guest stars, novae or supernovae, that flared up in the sky. In the Americas, the Maya civilization, at its height between about 250 and 900 CE, crafted elaborate calendars rooted in celestial cycles. They observed the motions of Venus with particular care, timing certain wars and rituals to the planet's appearances as morning or evening star. They built observatories, such as the Caracol in Chichen Itza, with windows aligned to the equinox sun and the extremes of Venus's rise and set. Though separated by great distances and cultures, these civilizations all found order and guidance in the sky. Careful skywatching became a universal language of timekeeping and prophecy. By the time of classical Greece, around 500 BCE and onward, the accumulated astronomical knowledge of older civilizations was being absorbed and reinterpreted through the lens of Greek philosophy and geometry. Greek scholars traveled to Babylon and Egypt, learning about calendars, star catalogues, and mathematical techniques developed there. They brought home ideas like the 19-year Metonic cycle for harmonizing lunar and solar calendars, and they adopted the Babylonian division of circles into 360 degrees. The Greeks began to seek not just patterns, but principles. As early as the 6th century BCE, Pythagoras and his followers suggested that nature was built on numbers, and that the motions of the heavens might follow mathematical harmony. By the 4th century BCE, Aristotle taught that Earth was a sphere, noting the curved shadow it cast on the moon during eclipses, and placed Earth at the center of a finite cosmos of concentric crystalline shells. Around 240 BCE, in Egypt, Eratosthenes calculated Earth's circumference with astonishing accuracy. This showed how quantifiable the cosmos could be when one combined observation with geometry. While most Greek thinkers accepted a geocentric cosmos, there were noteworthy exceptions. In the 3rd century BCE, Aristarchus of Samos proposed that the Earth and other planets actually orbited the Sun. His heliocentric theory was far ahead of its time and gained little traction then, but it shows that the concept of a sun-centered system existed well before Copernicus. Meanwhile, Greek astronomers continued to refine the observational side of astronomy. In the 2nd century BCE, Hipparchus of Nicaea compiled a star catalogue of roughly 1,000 stars, noting their positions and brightnesses. He noticed that the positions of stars were not entirely fixed over long periods. By comparing his catalogue to observations from a century or more earlier, he discovered the gradual wobble of Earth's axis, known as the precession of the equinoxes. The level of precision the Greeks achieved with simple instruments, like sighting tubes and graduated circles, was remarkable. By the dawn of the 1st millennium AD, the sky had been charted and measured as never before, and intricate geometrical models, with circles and epicycles, were being used to predict the motions of the planets. All these developments set the stage for a towering synthesis. In the 2nd century AD, in Alexandria, Egypt, a great center of learning of the ancient world, an astronomer named Claudius Ptolemy would take up this rich legacy of observations and theories. He would create an encompassing model of the cosmos that would endure for over a millennium. The era of the first sky watchers, of stone circles and star lore, had evolved into an era of calculated predictions and celestial charts. The transition from mythology to science was gradual, but by Ptolemy's time, it was in full bloom. The story of astronomy was about to enter a new chapter, as the old Earth-centered ideas reached their most refined form, awaiting the challenge of a sun-centered revolution to come. In the 2nd century AD, in the city of Alexandria, an astronomer named Claudius Ptolemy set out to synthesize all existing astronomical knowledge into a single system. Drawing on observations from Greece, Babylonia, and his own era, Ptolemy crafted a grand model of the cosmos, with Earth immovably at its center. This geocentric model would dominate human thought for over a millennium. It was both mathematically elaborate and philosophically satisfying to the people of that time. Earth, in Ptolemy's universe, was the hub of all celestial motion, a natural assumption, since it feels as if the ground beneath us is still, and everything in the sky turns around us. In Ptolemy's model, the Earth was orbited by a series of concentric spheres. Nearest was the Moon's sphere, circling Earth roughly once a month. Next came Mercury, then Venus, each on its own transparent shell. Beyond them, the Sun itself revolved around Earth in a daily journey that brought day and night. Farther out were the spheres of Mars, then Jupiter, then Saturn, the outermost planets known in antiquity, each taking longer to complete its circuit. Finally, at the greatest distance, lay the sphere of the fixed stars, an immense shell on which all the constellations were embedded, rotating daily to produce the rising and setting of stars. Some philosophers even imagined an outermost layer, the prime mover that gave the entire cosmic system its motion. To people of Ptolemy's time, this structured, Earth-centered cosmos was comforting and ordered. The heavens were finite, noble, and revolving with Earth and humanity at the focal point. But the planets, the wandering stars, posed a challenge. Observers for centuries had noted how planets like Mars and Jupiter did not move at a steady pace along their paths. At times, a planet would slow down, halt, and even drift backwards, retrograde, for a while before resuming its forward motion against the background stars. How could this be? Ptolemy's ingenious solution was to introduce a system of circles upon circles. He supposed that each planet moved in a small circle of its own, an epicycle, even as it travelled on a larger circle, called a deferent, around Earth. By tuning the sizes and speeds of these epicycles, Ptolemy could account for the looping, backtracking paths of the planets. This mathematical contrivance made the geocentric model quite accurate in its predictions. Using Ptolemy's tables and algorithms, one could predict where, say, Mars would appear in the sky on a given date, or when Venus would be visible at dawn or dusk. For the needs of calendar makers, navigators, and astrologers, the system was sufficiently precise. Ptolemy presented his comprehensive model in a work that later generations called the Almagest, meaning the greatest. The Almagest was a treatise encompassing all aspects of astronomy as known to the Greco-Roman world. In it, Ptolemy detailed the geocentric model's mechanics and provided step-by-step instructions for calculating celestial positions. He included a star catalogue with over 1,000 fixed stars, listing their coordinates and brightness, a legacy of earlier astronomers. The Almagest became the astronomical Bible for scholars from its publication in the 2nd century AD through the medieval era. Long after the Roman Empire fell, astronomers in the Islamic world translated and studied Ptolemy's work. They called it Al-Magisti and expanded upon it. It crossed into medieval Europe via those Arabic translations and formed the foundation of astronomy taught in universities. For century upon century, to question Ptolemy's model was to question the accepted understanding of the cosmos itself. Part of the model's enduring power was how well it harmonized with philosophical and religious ideas. In Ptolemy's time, and for long after, it was believed that the celestial realm was fundamentally different from Earth. Earth was the realm of change and decay, but the heavens beyond the moon were perfect and unchanging. Circular motion was seen as the most perfect, divine form of movement. Ptolemy's system, with planets on crystalline spheres, moving in circles, aided by epicycles, fit that ideal. It also placed Earth at the center. Later, medieval Christian thinkers would adopt this cosmology wholeheartedly, embedding the Earth-centered cosmos into a theological framework. Earth, with mankind, was at the center of creation, and the celestial spheres were the abode of angels and God. The Ptolemaic cosmos was thus not only a physical model, but a deeply moral and spiritual one. It gave people the sense that they knew their place in the universe, at the center, fixed and significant, with the cosmos literally revolving around them. Ptolemy's model proved resilient. Through the centuries, as observations became more precise, scholars tweaked the system, adding a small epicycle here or adjusting a sphere's speed there to better match new data, rather than abandon the Earth-centered scheme. In the medieval Islamic world, astronomers like Al-Tusi and al-Battani refined Ptolemaic calculations and even pointed out inconsistencies, like subtle changes in the moon's motion. Yet the core framework remained unchallenged. In Europe, the Ptolemaic model, merged with Aristotelian physics, became dogma. It was taught alongside scripture as the obvious order of God's creation. By the 15th century, however, the compounding of minor discrepancies and the sheer complexity of the epicycle-laden model made some thinkers uneasy. The cosmic machine, built of dozens of interlocking circles, had grown cumbersome. There was a growing sense that nature's true design might be simpler than this artifice. The stage was set for a radical rethinking of the cosmos, one that would shift the center of the universe from Earth to the Sun. In the early 1500s, a Polish cleric and scholar named Nicholas Copernicus quietly developed a radical theory that the Sun, not Earth, was at the center of the known universe. After years of study and calculation, he concluded that placing the Sun in the middle made the motions of the planets far more orderly. In his heliocentric model, Earth became one of the planets, orbiting the Sun just as Venus or Mars did. The Moon alone continued to circle Earth, but all the other planets revolved around the Sun. Copernicus also proposed that Earth spins on its axis once a day, causing the daily rising and setting of the Sun, stars, and planets. This simple shift, a moving Earth and a stationary Sun, was a revolutionary change in perspective, one that Copernicus knew would be controversial. Copernicus was cautious about broadcasting his idea. For decades, he circulated his heliocentric theory only among friends and fellow scholars. He waited until 1543, the year of his death, to publish his great work on the revolutions of the heavenly spheres. According to later tales, Copernicus received the first printed copy on his deathbed. Whether fact or legend, the heliocentric theory had finally entered the public arena. Initially, however, it did not cause an uproar. To most learned contemporaries, Copernicus's proposal was seen as a useful mathematical hypothesis, not necessarily as a literal description of the cosmos. After all, if Earth was hurtling through space, why didn't people feel it move? Why didn't objects fly off the spinning globe? And if Earth orbited the Sun, why did the constellations not change their positions over the year, the expected parallax effect? Copernicus and his supporters argued that the stars were so distant that any parallax was too small to detect with the naked eye, implying a universe vastly larger than previously imagined. Even so, many scholars remained skeptical. And since Copernicus still assumed the planets moved in perfect circles, his model, while conceptually simpler, did not dramatically improve the accuracy of planetary predictions at first. It was a bold idea that lacked solid observational proof in its early years. Over time, the Copernican model began to attract a few bold advocates who saw an elegant truth in it. They viewed the sun-centered system as a beautiful simplification of the cosmic mechanism, a graceful clockwork that no longer required awkward adjustments. To these early heliocentrists, it was as if the cosmic stage had been rearranged to put the brightest actor, the sun, at the center, and everything made more sense as a result. But the idea remained largely theoretical until further evidence could be found. By the early 1600s, that evidence was on the way. The stage was set for new discoveries, both observational and theoretical, that would firmly vindicate Copernicus's vision. A new generation of astronomers was coming, armed with the telescope and guided by mathematics, ready to transform the Copernican hypothesis into demonstrable reality. In 1609, the same year that Johannes Kepler published his first two laws of planetary motion, an Italian mathematician named Galileo Galilei pointed a new invention toward the night sky. The invention was the telescope, a simple tube with lenses, and for the first time in history, human eyes saw the heavens magnified. Galileo's observations would open a new chapter of astronomy. When he looked at the moon, he saw mountains and craters. Realizing that the moon was not a perfect, ethereal orb, but a world with terrain much like Earth, he turned his telescope to the planet Jupiter and was astonished to find 4 small stars orbiting it. In reality, 4 moons circling a planet, a miniature planetary system. This clearly showed that not everything in the cosmos revolved around Earth. Night after night, Galileo sketched the positions of these Jovian moons as they moved around Jupiter, providing undeniable evidence of orbital motion around a center other than Earth. Everywhere Galileo looked, he challenged old assumptions. He observed that Venus went through a full cycle of phases, from a thin crescent to a full disk and back, just like the moon. The Ptolemaic geocentric model could not easily explain that phenomenon, but the Copernican heliocentric model could. In a sun-centered system, Venus circles the sun on an orbit inside Earth's, and we see different portions of its sunlit half as it moves around, exactly what Galileo observed. He also noticed spots on the sun, blemishes that appeared and vanished and drifted across the solar disk. This was evidence that the sun itself rotated, and that it was not the flawless, unchanging body philosophers had imagined. Even the planet Saturn perplexed him. His telescope showed odd lobes or ears on either side of Saturn. We now know he was glimpsing Saturn's rings, though his instrument was too crude to discern them clearly. And when Galileo trained his telescope on the Milky Way, what looked to the naked eye like a milky cloud resolved into countless faint stars. The universe, it appeared, held far more stars than could be seen without aid, and they were scattered across immense distances. Galileo eagerly published his discoveries in 1610 in a booklet titled The Starry Messenger. The news spread quickly across Europe. Some greeted it with wonder and excitement. The cosmos was not what they had assumed. Others, especially certain authorities in the Catholic Church, met Galileo's findings with skepticism and hostility. The idea that Jupiter had moons, or that the sun had spots, wasn't inherently heretical, but Galileo's further conclusion, that these discoveries supported Copernicus's sun-centered model, was more troubling. It threatened the established worldview and the authority of those who had embraced the old Ptolemaic system. Over the next 2 decades, Galileo entered into public debates and wrote dialogues arguing for the new astronomy. Eventually, this boldness brought him before the Inquisition. In 1633, under threat of severe punishment, Galileo was forced to recant his advocacy of heliocentrism. According to a famous but possibly apocryphal story, after he recanted, he muttered, "Eppur si muove," and yet it moves, asserting that, recantation or not, Earth does move around the sun. Whether or not he actually said those words, the truth of the heliocentric system was by then becoming ever harder to deny. Galileo spent the final years of his life under house arrest. Blind, but still mentally active, continuing to write about physics. Despite his personal suffering, the foundation had been laid. The telescope had forever changed astronomy, and Galileo's discoveries had given the Copernican model tangible, public evidence. No longer was heliocentrism just an elegant idea in a book. It was supported by observation. Moons circling another planet, phases of Venus, a sun that rotated and was imperfect. The tide was turning. Even within the church and among learned men across Europe, the realization was dawning that Ptolemy's cosmology might be wrong. A new generation of astronomers continued Galileo's work with improved instruments, discovering, for example, additional moons and noticing subtle deviations in planetary orbits that begged for a new explanation. Meanwhile, Johannes Kepler, working hundreds of miles away in Germany, was solving the puzzle of planetary motion using the decades of observations made by Tycho Brahe. Kepler had been Tycho's assistant in Prague and inherited a treasure trove of the most accurate planetary data ever recorded, all gathered without a telescope, using giant protractors and sighting tools. Tycho had painstakingly plotted the positions of planets night after night, with particular focus on Mars, whose motion was the most puzzling. After Tycho's untimely death in 1601, Kepler took on the task of making sense of Mars's orbit, a problem that had baffled astronomers for centuries. Kepler tried and failed, again and again, to fit Mars's path to combinations of circular motions, as tradition insisted it must be. The data simply refused to line up with any arrangement of circles. Finally, Kepler broke with a millennia-old dogma. He abandoned the idea of perfect circular orbits and tried an oval shape, an ellipse. To his amazement, this change made everything fall into place. Mars's observed positions over the years traced an ellipse with the Sun at one focus. This breakthrough became Kepler's first law of planetary motion. Planets orbit the Sun in ellipses, not circles. Kepler soon discovered a second law as well. He found that as a planet moves along its orbit, it sweeps out equal areas in equal times. In practice, this means a planet travels faster when it is nearer the Sun and slower when it is farther from the Sun in its orbit. Kepler published these first two laws in 1609, fundamentally redefining celestial mechanics by showing that the planets' paths were not perfect circles, but ellipses governed by discernible rules. A decade later, in 1619, Kepler added a third law, connecting the motions of different planets in one elegant mathematical relationship. He discovered that the square of a planet's orbital period, the time it takes to complete one orbit of the Sun, is proportional to the cube of its average distance from the Sun. In simpler terms, the farther a planet is from the Sun, the more slowly it travels in its path, and not arbitrarily slower, but following a precise formula. This law hinted at a deep harmony in the solar system. Kepler called it the music of the spheres, imagining a cosmic symphony in which each planet's orbit was a musical note in the Sun's grand harmony. Kepler's laws, based on Tycho's data and his own genius for patterns, described the solar system's motions with unprecedented accuracy. Yet even Kepler did not know why the planets moved as they did. He had answered the question of how the planets move, but the underlying cause, the force, driving them, remained a mystery. That explanation would come later, from Isaac Newton. But by the early 17th century, thanks to Galileo's telescopic evidence and Kepler's mathematical laws, the heliocentric model had transformed from a controversial hypothesis into the foundation of a new understanding of the cosmos. The dawn of modern astronomy had truly arrived, a time when careful observation and mathematical reasoning together began to unlock the secrets of the heavens. The stage was now set for the next great insight, one that would tie together the motions of the heavens and the motions on Earth under a single, elegant theory. On a plague-haunted evening in the 1660s, a young Isaac Newton sat in the countryside of England, watching an apple fall from a tree. This simple observation sparked a profound question in his mind. Could the same force that pulled the apple to the ground also reach all the way to the moon? Newton, a brilliant yet reclusive thinker, set about formulating a revolutionary idea: that a single universal force governs the motion of both earthly objects and celestial bodies. By the late 17th century, Newton had developed 3 laws of motion and a law of universal gravitation, uniting the physics of the heavens and the earth. In one sweeping framework, he explained why planets orbit the sun and why the moon orbits Earth, as well as why an apple falls downward and not sideways. It was a moment of synthesis that scientists and philosophers had long dreamed of. The revelation that the cosmos is bound together by the same natural laws everywhere. Newton's laws of motion provided the foundation. He described how objects move and interact. A body remains in steady motion or at rest unless acted upon by a force, inertia. A force causes a change in motion proportional to the mass of an object, encapsulated in the equation F(x)m(a). And for every action, there is an equal and opposite reaction. These simple principles could describe a cannonball's arc through the air or the orbit of the moon with equal precision. But it was Newton's insight into gravity that truly unveiled a universal harmony. He proposed that every mass in the universe attracts every other mass with a force that diminishes with the square of the distance between them. This was the law of universal gravitation. Using this law, Newton proved mathematically that the very same gravitational pull that causes an apple to drop from a branch will compel the moon to continually fall around Earth rather than fly off into space. In other words, the moon is forever falling toward Earth, but because it also has sideways motion, it falls around Earth and thus orbits. Gravity, Newton realized, is the invisible hand that guides the planets in their courses and choreographs the dance of moons and comets. It is a force that operates on Earth and in the heavens alike, binding the universe into one law-governed system. In 1687, Newton published his masterwork, the Philosophiae Naturalis Principia Mathematica, Mathematical Principles of Natural Philosophy, known simply as the Principia. In it, he laid out his laws of motion and gravity and demonstrated that Kepler's laws of planetary motion were natural consequences of these deeper principles. The Principia showed that the elliptical orbits of planets, the swing of the moon around Earth, and even the path of a comet were all explicable by one universal law. It was a staggering achievement. Suddenly, the cosmos seemed knowable and orderly, as if a grand clockwork, previously veiled, had been revealed. Astronomers could now use Newton's equations to predict phenomena with unprecedented accuracy. The return of Halley's comet. Newton's friend Edmund Halley did exactly that, predicting the comet's return in 1758. The ebb and flow of ocean tides caused by the moon's gravity, or the slight perturbations in Saturn's motion due to Jupiter's pull. Celestial events no longer required separate explanations or the hand of capricious gods. They were all part of a single physical system. Newton's work completed the Copernican revolution. With a comprehensive physical explanation for why planets orbit as they do, the sun-centered model was no longer a mere geometric convenience, but a dynamic reality governed by universal laws. In Newton's universe, the same physics applied everywhere. A stone tossed in the air on Earth and a planet orbiting the sun both obeyed the same principles of motion. This unity was inspiring and even spiritual to Newton's contemporaries. Many spoke of a clockwork universe, a grand mechanism created perhaps by a divine clockmaker, set in motion and left to run according to its natural laws. To Newton himself, uncovering gravity and motion was a way to glimpse the clockwork of God's creation. He humbly described his insights as thinking God's thoughts after him. The influence of Newton's discoveries on astronomy and science was immense. Future astronomers would use his mathematics to dive even deeper into the cosmos. In the centuries after Newton, his laws led to the discovery of new planets. For example, perturbations in Uranus's orbit led 19th century astronomers to predict and then find Neptune lurking beyond the range of naked eye vision. Newton's framework also allowed an understanding of phenomena far beyond the solar system. The idea that the universe is governed by universal principles set the stage for all subsequent physics and astronomy. By the end of the 17th century, thanks to Newton, the cosmic dance of planets and moons was no longer a mystery choreographed by unseen spirits, but a predictable ballet ruled by gravity and motion. Humanity had discovered a universal harmony in nature, a set of laws that applied from an apple falling in an orchard in England to the planets swinging through the void. It was a triumph of human reason and observation, marking the true beginning of modern science's confidence in comprehending the cosmos. Newton's era closed a chapter in astronomy. The basic framework of the solar system and its governing laws were now understood. But even as Newton's achievements answered age-old questions, new ones emerged. What were the stars made of? How far away were they truly? Was the sun just one star among countless others? And what were those faint, cloud-like patches, nebulae, that telescopes were beginning to reveal in the night sky? As the 18th century turned to the 19th, astronomers stood ready to tackle these mysteries. They would do so with new tools and new physics, kicking off yet another revolution in our perception of the cosmos. By the dawn of the 19th century, astronomers had a solid grasp of the solar system's layout and the laws governing planetary motion. But the stars beyond remained mysterious lights, their distances, compositions, and natures unknown. Two new tools of that century would change that: the prism and the photographic plate. Through these, light itself would reveal the secrets of the stars, and the cosmos would be mapped on a scale never before imagined. One of the first breakthroughs came from dissecting starlight. In 1802, a British scientist noticed dark lines in the spectrum of sunlight when he spread it into a rainbow with a prism. Later, a German optician named Joseph von Fraunhofer mapped hundreds of these dark lines with precision. No one knew what they meant at first. It wasn't until 1859 that physicists Gustav Kirchhoff and Robert Bunsen in Heidelberg discovered the key. When they heated elements like sodium or hydrogen in a flame, they produced bright lines of color at specific wavelengths, a unique fingerprint for each element. Those same patterns of lines, seen as dark gaps against the sun's rainbow spectrum, meant those elements were present in the sun's outer layers, absorbing certain colors. Suddenly, the chemistry of the heavens opened up. Astronomers realized that the sun and stars were made of the same kinds of elements found on Earth. The iron in our blood, the calcium in our bones, these existed in the distant stars as well. Humanity learned that we share a common chemistry with the stars. This new science of spectroscopy, reading the coded light of stars, revealed astounding things. Helium, for example, was discovered in the sun's spectrum in 1868 during a solar eclipse before it was found on Earth. It was named after Helios, the Greek sun god. By comparing stellar spectra, astronomers found that stars came in different types. Some were hotter, some cooler, each with its own spectral signature. Father Angelo Secchi in the 1860s began classifying stars into groups by their spectra, a first attempt at identifying stellar types and temperatures. Decades earlier, the philosopher Auguste Comte had declared that humans would never know what the stars are made of. Yet now they did. The stars were no longer just points of light. They were physical objects, composed of the same atoms as Earth, blazing at thousands of degrees, each with its light carrying a story across space. The prism and spectroscope became a cosmic cipher, allowing astronomers to decode starlight and read the chemistry of distant worlds. While the prism unveiled the star's composition, the photographic plate revolutionized how we recorded and discovered celestial objects. Before photography, astronomers had to rely on drawings and human vision, which could only see so much and left no permanent record beyond sketches. But in 1839, the invention of practical photography changed everything. In 1840, John W. Draper took the first photograph of the moon, capturing details of its surface on a fragile daguerreotype plate. Over the following decades, as photographic techniques improved, astronomers began attaching cameras to telescopes. Unlike the human eye, a photographic plate could collect light over long exposures, revealing faint stars and nebula invisible to the eye. In 1850, the star Vega was photographed at Harvard Observatory, the first photograph ever taken of a star, aside from the Sun. By the 1880s, astronomers like Henry Draper were taking long-exposure images of nebulae. Draper's photograph of the Orion Nebula in 1880 showed wisps of cosmic gas and starlight in a detail no eye could ever see. Suddenly, the universe was unveiling itself on glass plates. Those images could be studied, measured, and kept for posterity, allowing astronomers to make discoveries that no one could grasp in a single night at the eyepiece. Photography didn't just capture pretty pictures, it vastly expanded star catalogues and enabled new discoveries. With sensitive plates and ever larger telescopes, 19th century astronomers conducted ambitious surveys of the sky. They catalogued hundreds of thousands of stars, far beyond the few thousand visible to the naked eye. For example, German astronomer Friedrich Argelander and colleagues published the Bonner Durchmusterung in the 1860s, charting the positions and brightness of over 300,000 stars in the northern sky. Similar surveys extended to the southern skies. The sheer scale of the stellar universe was coming into focus. Once, humanity knew only the stars as unchanging pinpoints overhead. Now each could be recorded, its brightness measured, its position fixed on a map. By 1890, the Henry Draper Catalogue, begun at Harvard College Observatory by a team that notably included several pioneering women astronomers, was classifying stars by their spectra. New variable stars were discovered on photographs, stars that mysteriously brightened and dimmed over time, hinting that physical changes and cycles were happening in distant suns. Bit by bit, the night sky was being quantified and understood in ways never before possible. Other 19th century breakthroughs further expanded our cosmic perspective. In 1838, astronomer Friedrich Bessel managed to measure the first reliable distance to a star, 61 Cygni, using parallax, the slight shift in a star's apparent position as Earth orbits the Sun. The angle he measured was tiny, but from it, Bessel calculated that 61 Cygni was over 10 light-years away, on the order of 100 trillion kilometers. This was stunning proof of the star's immense distances. It confirmed what Copernicus's followers had long suspected. If Earth's motion around the Sun produced no easily observed parallax in the stars, it was because the stars were incredibly far. Now, at last, The void between the stars had a measurable scale. Meanwhile, other observers found new planets in our own solar system: Uranus in 1781 and Neptune in 1846, and discovered moons around those worlds, as well as numerous asteroids and comets. The inventory of the solar system was growing, and with it, our understanding of our cosmic neighborhood. By 1900, astronomers had measured the size of Earth's orbit, the astronomical unit, gauged the distance to a few of the nearest stars, and begun to suspect that the Sun was just one star among many in an enormous city of stars we call the Milky Way. As the 19th century drew to a close, astronomy had transformed into astrophysics, a science not only of where objects are, but what they are and how they move. The universe felt larger and more dynamic than ever. The Milky Way's misty band of light was now understood to be the combined glow of billions of distant stars within our galaxy. Whether the faint spiral nebulae observed in some telescopes were separate galaxies far beyond our own or nearby swirling clouds of gas was still debated, a question poised on the brink of an answer. The groundwork was laid for the next great steps. As the 20th century dawned, ever bigger telescopes and bold new physical theories were on the horizon. Questions about the true scale of the universe, the nature of those mysterious nebulae, and even the fundamental fabric of space and time were about to find dramatic answers. The story of the cosmos was far from complete. A new chapter of discovery was about to begin, built upon 4 centuries of astronomical progress. From the first sky watchers and the first myths to the sciences of spectra and photographic light, humanity stood at the threshold of deeper cosmic understanding, ready to take another giant leap in revealing the cosmos. In the early 20th century, the universe seemed comfortably small to astronomers. They believed our Milky Way galaxy was all there is, an island of stars adrift in a vast darkness. The faint, fuzzy patches of light seen in the night sky were thought to be nearby clouds of gas or clusters of stars within our galaxy. The cosmos felt static and enclosed, with the Milky Way marking the boundaries of everything we could ever know. Some astronomers, however, dared to wonder if those faint nebulae were not nearby at all, but far beyond our galaxy, perhaps entire galaxies of their own, like distant islands of light. If true, it would mean the universe was far larger than anyone had imagined, filled with myriad island universes rather than just one. This notion was controversial and met with fierce resistance. Many in the scientific community couldn't fathom a cosmos bigger than the Milky Way. The question hung unanswered in the air, awaiting decisive evidence. On a crisp night in 1923, high atop Mount Wilson in California, astronomer Edwin Hubble set his gaze on the Andromeda Nebula. Using the most powerful telescope of the time, he captured photographs of that faint, spiral smudge of light. Night after night, he examined the plates for a special kind of star. At last, he spotted what he was seeking: a faint star in Andromeda that periodically brightened and dimmed. It was a Cepheid variable, a pulsating star that serves as a cosmic yardstick. Years earlier, Henrietta Leavitt had shown that by measuring a Cepheid's pulsation period, one could deduce its true brightness and thus its distance. Hubble applied this method, and the result came back staggering: over 1 million light-years. That star, which Hubble marked with an excited VR on his photographic plate, was far outside the Milky Way. Andromeda wasn't a nearby gas cloud at all. It was an entirely separate galaxy. With that single observation, the universe expanded dramatically in human understanding. Hubble had proven that our Milky Way was not alone. It was just one galaxy among many. The great debate over the nature of the nebulae was finally settled. In fact, just a few years earlier, in 1920, Harlow Shapley and Heber Curtis had famously argued this question. Shapley insisted those nebulae were part of our galaxy, while Curtis suspected they were distant galaxies. Hubble's discovery vindicated Curtis. One by one, other spiral nebulae were likewise revealed to be galaxies in their own right, each a swirling island of billions of stars. What had once been the entirety of the known cosmos, our single galaxy, became only a tiny drop in a vast sea. The cosmic ocean was far more vast and filled with these islands of light than anyone had ever imagined, stretching away into depths we had only begun to fathom. It was a humbling expansion of perspective. The scale of creation had grown immensely in our minds. Decades of observations after Hubble's discovery brought another surprise. As astronomers measured the motions of those myriad galaxies, they noticed almost all were flying away from us. The light from distant galaxies was shifted toward longer, red wavelengths, a Doppler effect indicating they were receding at great speed. Even more astonishing, the farther a galaxy was, the faster it seemed to flee. This pattern, now known as Hubble's law, revealed a fundamental truth. The universe itself is expanding. Space was stretching, carrying galaxies apart like raisins in rising bread dough. At first, the notion of an expanding cosmos was difficult to grasp. Even Albert Einstein, whose general theory of relativity allowed for dynamic universes, initially resisted the idea. He had introduced a cosmological constant into his equations to hold the universe static, later calling that adjustment his biggest blunder once expansion was confirmed. But the evidence was clear. Our universe is not eternal and unchanging. It is evolving over time. If galaxies are rushing apart now, it stood to reason that long ago they must have been much closer together, perhaps even on top of one another, in an unimaginably dense state. Indeed, in 1927, Belgian astronomer Georges Lemaitre had already suggested exactly that. Using Einstein's equations, he theorized that the cosmos began in a hot, compact, primeval atom that exploded outward. In time, scientists began to embrace this bold idea. What if the universe started with a brilliant, fiery flash, a kind of primordial explosion that set all of space expanding? This concept, nicknamed the Big Bang, a term coined derisively by astronomer Fred Hoyle in 1949, gradually took hold as the leading story of cosmic origins. Yet not everyone was convinced at first. A rival hypothesis, the steady-state theory, argued that as the universe expands, new matter is continuously created, so the overall appearance of the universe remains unchanged over time. For a while, the debate continued. A universe with a beginning in time was a radical idea, with almost philosophical implications, and many sought concrete proof of the Big Bang. Cosmologists realized that if the Big Bang model were true, there should be some remaining glow from that hot, early state, a faint background light filling space. They calculated that over billions of years of expansion, such light would have cooled to just a few degrees above absolute zero and shifted into the microwave part of the spectrum. All that was needed was to detect it. Then, in 1965, a faint whisper of cosmic creation was finally heard. Two young radio astronomers in New Jersey, Arno Penzias and Robert Wilson, were testing a large horn-shaped antenna when they encountered a persistent hiss of microwave noise. This annoying background signal appeared no matter where they pointed the antenna, night or day. Perplexed, they checked and rechecked their equipment. They even climbed into the horn to shoo away some pigeons roosting inside and clean out the droppings, suspecting the birds might be the cause of the interference. But still, the mysterious hiss remained. At the same time, not far away at Princeton University, physicist Robert Dicke and his colleagues had been searching for exactly such a signal. When Penzias and Wilson learned of Dickey's work, everything clicked into place. The uniform glow they had found was the cosmic microwave background radiation, the very afterglow of the Big Bang. Space was aglow with the residual heat from the universe's birth. Upon hearing of the discovery, Dickey famously quipped, "Well, boys, we've been scooped." For the first time, humans had direct evidence that the early universe was incredibly hot and dense. The cosmic microwave background, or CMB, was like a baby picture of the universe, showing it as it looked only 380,000 years after the Big Bang. It confirmed beyond any reasonable doubt that our cosmos began in a tremendous explosion of light and has been expanding and cooling ever since. The discovery earned Penzias and Wilson the 1978 Nobel Prize in Physics. In subsequent decades, satellites such as COBE, WMAP, and Planck mapped the CMB in exquisite detail. They found that it has an almost perfectly uniform temperature of about 2.7 K, just above absolute zero, exactly the blackbody spectrum predicted by Big Bang theory. Within that uniform glow, the satellites also detected tiny ripples, minute fluctuations only a few millionths of a degree in temperature. These slight irregularities are the seeds from which galaxies and clusters later grew. The message of the CMB was clear and breathtaking. The universe had a fiery origin, and echoes of that creation event still surround us, coming from every direction in the sky. Even with the triumph of the Big Bang theory, another deep mystery lurked in the cosmos, something invisible yet immensely influential. Astronomers gradually realized that the universe's visible matter is only a small part of the story. Galaxies and clusters were moving and behaving as if they contained far more mass than we could see. The first hint of this dark matter came in the 1930s from Swiss astronomer Fritz Zwicky. He studied the Coma cluster of galaxies and found that galaxies there were zipping around so fast the cluster ought to fly apart. The gravity of all the visible stars and gas in the cluster wasn't nearly enough to hold it together. Zwicky concluded there must be a great deal of unseen mass providing the needed gravitational glue. His contemporaries largely overlooked this bold idea, but he had glimpsed a fundamental component of the universe. Decades later, in the 1970s, American astronomer Vera Rubin and her colleague Kent Ford uncovered more evidence of dark matter, this time within individual galaxies. Rubin measured how fast stars were orbiting in the outer regions of the Andromeda galaxy and many other spiral galaxies, and made a baffling discovery. The stars far from the galactic center were moving just as quickly as stars nearer in. According to Newtonian gravity, stars at a galaxy's outskirts should orbit more slowly if most of the mass is concentrated in the center, where the visible stars are. But in Andromeda, the expected drop-off in speed never came. The rotation curve was flat. It was as if some invisible matter in and around the galaxy was providing extra gravitational pull on those outer stars. The conclusion was inescapable. Enormous amounts of unseen mass, dark matter, permeate and envelop each galaxy. Rubin's findings, initially met with skepticism, were soon confirmed in galaxy after galaxy. The variety of rotation curves observed all pointed toward the same idea. A halo of dark matter surrounds each galaxy, far outweighing the visible stars within it. Dark matter has fundamentally reshaped our picture of the cosmos. Without it, the early universe might never have formed galaxies as quickly as it did. Dark matter's gravity was the scaffold on which ordinary matter collected. In the early universe, clumps of dark matter pulled in normal gas, seeding the formation of galaxies and galaxy clusters. Today, astronomers map the distribution of dark matter indirectly by observing how its gravity bends and distorts the light of distant objects, a technique called gravitational lensing. A dramatic example occurred in a system called the Bullet cluster, where two galaxy clusters collided. In the aftermath, the hot gas from each cluster, which is ordinary matter, was left behind, but the regions of strongest gravity, inferred from lensing, had moved on ahead, indicating the dark matter passed through and separated from the visible gas. This kind of observation is a direct, visual proof of dark matter's existence. Yet despite decades of study, the true nature of dark matter remains elusive. What is it made of? It doesn't emit light, so we can't see it. It barely interacts with regular atoms, so it's like a ghost in our laboratories. It could be composed of exotic, as yet undetected particles that swarm through the universe and through us without a trace. Physicists have built large underground detectors, quiet laboratories under mountains or deep in mines, hoping that on very rare occasions a dark matter particle might collide with an atomic nucleus and produce a tiny flash of light or electric signal. So far, these experiments have not conclusively detected anything. Powerful particle accelerators, like the Large Hadron Collider, have also not yet produced any new particle that could be the dark matter. Ideas abound. Perhaps dark matter consists of heavy, slow-moving particles nicknamed WIMPs, weakly interacting massive particles, or ultralight particles resembling ghosts, or something even stranger, like primordial black holes. Around the world, scientists continue to chase this shadowy matter. We know it's there, its gravity gives it away, but until we actually identify a dark matter particle, it remains a profound mystery and a reminder of how much we still don't know about the universe. As if dark matter weren't mystery enough, the late 20th century delivered an even bigger shock. Astronomers believed that although the universe is expanding, the mutual gravity of galaxies should be slowing that expansion over time. The big question was, how much is it slowing down? Would the expansion someday stop and reverse into a big crunch? Or would it continue forever at a gradually decreasing rate? To find out, in the 1990s, two international teams of astronomers set out to measure the cosmic deceleration by observing distant exploding stars known as Type Ia supernovae. These stellar explosions can serve as standard candles. They have a known intrinsic brightness, so by comparing how bright they appear, one can gauge their distance and the expansion rate of the universe when the light was emitted. The results of this painstaking search were completely unexpected. In 1998, both teams, studying supernovae billions of light years away, announced that instead of slowing down, the expansion of the universe is speeding up. The distant supernovae were fainter, and hence farther away, than they would be in a decelerating universe. The only reasonable explanation was that some mysterious repulsive force is pushing the universe outward faster and faster. This was a stunning revelation, an accelerating universe, flying in the face of all expectations. It implied that our cosmos, far from being reined in solely by gravity, is dominated by something else, something that overwhelms gravity on cosmic scales. The unknown agent driving this acceleration was dubbed dark energy. Just as with dark matter, the word dark really means unknown, rather than literally dark. And energy refers to the fact that it seems to be a property of space itself, an energy inherent to the vacuum of space that causes a repulsive effect. It even recalls Einstein's cosmological constant, the very term he invented to keep the universe static. Ironically, Einstein's blunder may have been prescient. The best explanation for dark energy today is that it is indeed a cosmological constant, a small but pervasive energy woven into the fabric of spacetime. Subsequent observations soon supported this strange picture. Detailed maps of the cosmic microwave background and surveys of galaxy clustering all pointed to a universe dominated by dark energy. By current estimates, about 68% of the cosmos is dark energy, 27% is dark matter, and only about 5% is normal matter, the atoms that make up stars, planets, and people. In essence, everything we see, all the galaxies, stars, and glowing gas clouds, is just a tiny fraction of what exists. Dark energy appears to be smoothly distributed and constant in its effect, filling space with a gentle pressure that becomes significant only over tremendous distances. It doesn't noticeably affect the scale of galaxies or even clusters. Gravity holds those together. But across billions of light years, the repulsive push of dark energy wins out and speeds up the expansion. Teams of astronomers worldwide are measuring the expansion history of the universe with exquisite precision, hoping to learn whether dark energy has always been constant or might evolve over time. So far, it behaves very much like Einstein's cosmological constant, but its origin remains utterly puzzling. The discovery of dark energy has profound implications for the fate of the universe. If dark energy continues to dominate and behaves as it does now, the expansion of the universe will keep accelerating. In the far future, galaxies that are not gravitationally bound to us will rush away at ever-increasing speeds. Trillions of years from now, an observer in our galaxy's vicinity might see nothing but darkness. Distant galaxies will have receded beyond the horizon of visibility. Our Milky Way, by then perhaps merged with its neighbours, would be an isolated oasis of stars in an enormous void. This is often called the Big Freeze scenario, an endlessly expanding, gradually cooling universe fading into blackness. On the other hand, some theorists speculate dark energy might increase in strength over time. In extreme models, the so-called Big Rip, even galaxies, stars, and eventually atoms could be torn apart in the very distant future. Current observations don't favour such a dramatic ending. Dark energy looks constant, but we cannot be sure without a deeper understanding of what it is. This accelerating universe was a completely unanticipated twist in our cosmic story. It earned the leaders of the two supernova teams the 2011 Nobel Prize in Physics. More importantly, it opened yet another frontier of ignorance for scientists to tackle. What is this dark energy that composes roughly 2/3 of the universe? Is it truly Einstein's cosmological constant, an immutable property of space? Or is it something like a new field or force that can vary in time and space? At present, we simply don't know. Once again, just when we thought we had a handle on the contents of the cosmos, the universe threw us a curveball, reminding us that we have much more to learn. By the end of the 20th century, our conception of the universe had transformed. We discovered that our Milky Way is just one of countless galaxies. We found that the universe is expanding from a hot origin and is largely composed of dark matter and dark energy that we cannot directly see. We learned that even the life cycles of stars connect to us. The iron in our blood and calcium in our bones were forged in supernovae. Each breakthrough has brought us a deeper understanding of our cosmos, and at the same time, unveiled new mysteries. Yet even as astronomers puzzled over the invisible mass and energy dominating the universe, they were also turning to a more hopeful quest, the search for worlds beyond our solar system, and perhaps life beyond Earth. As astronomers studied these stellar cataclysms, they also turned to a more hopeful quest, the search for worlds beyond our solar system. For millennia, humans have gazed at the stars and wondered if those points of light might have worlds of their own. Visionaries like the 16th century philosopher Giordano Bruno even suggested that the universe is filled with innumerable suns and planets, a bold notion in an age when such ideas were deemed heretical. But for centuries, this remained unproven speculation. The first definitive breakthrough came in the early 1990s. In 1992, radio astronomers Alexander Wolszczan and Dale Frail announced the discovery of two planets orbiting an unlikely star, a pulsar, the tiny, rapidly spinning neutron star left over from a supernova explosion. Finding planets around a dead star was a shock. These were charred cinders circling a stellar corpse, blasted by intense radiation. But it was the first solid evidence that planets exist beyond our solar system. Then, in October 1995, a discovery truly opened the floodgates. Swiss astronomers Michel Mayor and Didier Queloz revealed they had detected a planet circling 51 Pegasi, a sun-like star about 50 light-years away. This was the first exoplanet confirmed around a normal star like our Sun. The planet, called 51 Pegasi b, defied expectations. It turned out to be a gas giant, about half the mass of Jupiter, but extremely close to its star, whipping around its orbit in just over 4 days. Such a hot Jupiter was completely unlike anything in our solar system. Initially, some were skeptical that a planet could exist in such a hellishly hot orbit, but follow-up observations quickly confirmed it. The era of exoplanet discovery had begun. Planet hunters around the world sprang into action, and excitement replaced skepticism as it became clear that other planetary systems were not only real, but might be very different from our own. After that, new exoplanets began turning up rapidly. In the late 1990s and early 2000s, dozens were found by various teams using the wobble of stars, the Doppler shift of starlight, to infer the presence of orbiting planets. Many of the early discoveries were also giant planets in tight, blistering orbits. Selection's bias made those easiest to find. These discoveries overturned our prior assumptions. We found gas giants skimming the surfaces of their stars, where no Jovian planet should be. We found planets in eccentric, elongated orbits that would take them from near their star to far out and back again. Some stars had multiple giant planets in complex gravitational resonances. Each new find was a revelation that nature could form planetary systems in wildly different configurations than the neat clockwork of our solar system. The variety of worlds out there hinted that our own solar system, once the template for all others, might actually be something of a cosmic oddball. The pace of discovery accelerated enormously with the launch of NASA's Kepler Space Telescope in 2009. Kepler stared unblinkingly at one small patch of sky in the constellations Cygnus and Lyra, monitoring about 150,000 stars continuously for 4 years. It searched for the tiny dips in a star's brightness caused when a planet transits, passes in front of, its star. From Kepler's data, astronomers eventually identified thousands of planet candidates. This single mission revealed that planets are astonishingly common. Most stars have at least one planet. Many have entire families of planets. Kepler showed that smaller planets, from Earth-sized up to a few times Earth size, are particularly abundant, even more common than giant planets. Suddenly, the night sky became richer. Each star we see isn't just a point of light, but potentially a sun with its own family of worlds. Every twinkling star became a place where planets might be orbiting, each world with its own environment and story. As of now, roughly 3 decades after the first exoplanet discoveries, astronomers have confirmed over 5,000 exoplanets orbiting other stars. These include a staggering variety of worlds. Giant gas planets, larger than Jupiter, icy Neptune-like planets, rocky super-Earths, a bit bigger than Earth, and even planets circling two stars at once, bringing to mind the twin sunsets of the fictional planet Tatooine. We've found scorched planets so close to their stars that their surfaces may be oceans of molten rock, and others so far from their suns that they are frozen ice balls. Some exoplanets orbit red dwarf stars so tightly that a year lasts only a few days, while others roam in distant orbits where their star is just a feeble spark. The diversity of these newfound worlds has astonished scientists. It shows that our solar system, while familiar to us, is just one peculiar example among a myriad of arrangements nature can produce. Among this menagerie of planets, a special few have captured our imagination, those that might resemble Earth. Astronomers have identified numerous exoplanets that lie in the habitable zone around their stars, the orbital region where temperatures could allow liquid water to exist on a rocky planet's surface. Some of these planets are tantalizingly close to Earth's size. For instance, the TRAPPIST-1 system, about 40 light-years away, boasts 7 Earth-sized planets, at least 3 of which are in or near the habitable zone of that dim red dwarf star. And in 2016, astronomers discovered an Earth-mass planet in the habitable zone of Proxima Centauri, the nearest star to our Sun, a mere 4.2 light-years away. These discoveries take the possibility of life beyond Earth from the realm of science fiction to something far more concrete. It's astonishing to consider. On some nights, the light arriving in our telescopes from those stars may have reflected off the oceans or clouds of planets that we cannot yet see. If conditions are right on some of these distant worlds, they could indeed harbour liquid water, and perhaps even simple life forms. We are now truly in the midst of the age of exoplanets. A generation ago, we didn't know for sure if other planetary systems existed. Now we know they are everywhere. This realization carries profound implications. It tells us that our solar system is just one of many, and perhaps not particularly special. Planet formation is a natural part of star formation, happening throughout the galaxy, and it raises the stakes for the age-old question of life elsewhere. Suddenly, the question, "Are we alone?" is not just philosophical, it's a scientific inquiry we can actively pursue. The cosmos feels more intimate and alive with possibilities than ever before. The search for new worlds and possible life continues with full vigor. NASA's Transiting Exoplanet Survey satellite, TESS, launched in 2018, is surveying almost the entire sky, focusing on closer, brighter stars to find more exoplanets, and it has already added hundreds to the catalogue. Meanwhile, the powerful James Webb Space Telescope, JWST, launched in 2021, is beginning to probe the atmospheres of some especially interesting exoplanets. JWST can gather the faint, filtered starlight that passes through a transiting planet's atmosphere and split it into a spectrum, detecting molecules like water vapor, carbon dioxide, and methane in those distant skies. In the coming years, astronomers hope to identify telltale biosignatures, chemical signs of life, such as oxygen or certain combinations of gases, in the air of Earth-sized planets orbiting within their stars' habitable zones. If such signs are found, it would suggest that life may have arisen on more than one world in the cosmos, a discovery that would fundamentally change our view of the universe. Looking further ahead, ambitious plans are on the drawing board for future observatories that could directly image Earth-like exoplanets. Concepts include space telescopes equipped with advanced internal coronagraphs, or even a large free-flying starshade that would be positioned tens of thousands of kilometers in front of a telescope to block a star's light. By blotting out the glare of the star, the telescope could directly see the faint glow of an orbiting planet. Such an instrument might one day take a true pale blue dot photograph of an Earth-like planet around a distant sun, a tiny bluish speck in the darkness, and analyze its light for signs of oceans, clouds, or even vegetation pigments. Though these missions are still decades away and technically challenging, the fact that we are even planning them shows how far our exploration has come. Not long ago, we could only speculate about other worlds. Now we're discovering them by the thousands, and even designing ways to search them for life. In parallel with the exoplanet revolution, astronomers were also opening an entirely new window on the universe, not through light at all, but through the subtle ripples of gravity. This development would usher us into the era of gravitational wave astronomy. Over 100 years ago, in 1916, Albert Einstein's general theory of relativity predicted that massive objects in motion should produce tiny ripples in the fabric of spacetime, gravitational waves. But Einstein himself wasn't sure we'd ever be able to detect them. He thought such waves would be far too weak to catch. For decades, the idea of gravitational waves remained a theoretical curiosity. Then in the 1970s, indirect proof arrived. In 1974, Russell Hulse and Joseph Taylor discovered a binary pulsar, two neutron stars orbiting one another, and found that their orbital period was slowly decreasing, exactly as Einstein's theory predicted it should, if the system were emitting gravitational waves. This observation earned the Nobel Prize in 1993 and gave astronomers confidence that gravitational waves were real and carried energy away as expected. Still, detecting them directly would be an enormous challenge. To detect gravitational waves directly, physicists constructed extraordinary observatories. The concept was simple in principle, but difficult in practice. Measure the minuscule stretching and squeezing of space caused by a passing gravitational wave. In the early 2000s, the United States built two facilities called LIGO, Laser Interferometer Gravitational Wave Observatory, one in Louisiana and one in Washington State, each consisting of two long arms, 4 kilometers in length, arranged in an L shape. A laser beam is split and sent down each arm, reflected by mirrors at the ends, and then recombined. If a gravitational wave passes through, it will momentarily stretch one arm and compress the other, changing the distance the laser travels by a tiny amount. By comparing the laser light from the two arms, scientists can detect that tiny difference. How tiny? LIGO was designed to sense changes in length much smaller than the width of a proton, an incredibly demanding measurement. Throughout the 2000s, LIGO went through upgrades to reach its design sensitivity. In the pre-dawn hours of September 14, 2015, this decades-long quest was finally rewarded. At 4:51 a.m. Eastern Time, the two LIGO detectors nearly simultaneously recorded a faint chirp signal lasting just a quarter of a second. The scientists who saw the signal knew immediately it was something extraordinary. They realized they had detected the death spiral of two merging black holes in a galaxy over 1 billion light-years away. Humanity had, at long last, directly detected gravitational waves. It was as if we had suddenly grown a new sense, ears to hear the universe. We were no longer deaf to the cosmos. For the first time, we could listen to the sound of space-time ringing from distant events. The signal matched exactly what Einstein's equations predicted for the final moments of two heavy black holes merging. These black holes were about 30 times the Sun's mass each, and they had been orbiting each other ever faster and closer, at the end, whirling at nearly half the speed of light, until they violently coalesced into one larger black hole. In that final fraction of a second, about 3 suns worth of mass was converted into pure energy in the form of gravitational waves. Those waves spread out and weakened over more than 1 billion years of travel. But by the time they reached Earth, LIGO could still sense them. The fabric of space here stretched and squeezed by a tiny amount, about 1 part in 10^21, causing a change in the length of LIGO's arms by a distance smaller than 1,000th the width of a proton. But that was enough. The LIGO instruments heard a distinctive chirp, rising in pitch and then abruptly stopping, which was the black hole's final orbital dance and merger. When scientists converted the signal to sound, it really did make a brief chirp, a fleeting note from an unimaginable cosmic symphony. For the first time, a ripple in space-time caused by a distant cataclysm had been measured on Earth. A curtain had lifted on a new era of astronomy, one that didn't rely on light at all. The announcement of this discovery came in February 2016, a century after Einstein's prediction, and it reverberated through the scientific world. The achievement was soon recognized with the 2017 Nobel Prize in Physics, awarded to 3 of LIGO's founding scientists. LIGO's success, however, rested on the dedication of hundreds of researchers and engineers from around the globe, working together for decades, a testament to human curiosity and teamwork. It was as if astronomy had gained a new sense organ. No longer were astronomers limited to observing the universe with electromagnetic waves, visible light, radio waves, X-rays, etc. Now we could directly sense the vibrations of space-time itself. With this new ability, the universe had much to tell us. In the months and years that followed, LIGO, joined by its European counterpart Virgo, detected numerous gravitational wave events. Most were additional mergers of black holes of various sizes, ringing space-time like cosmic bells. Each detection provided unique insights into the population of black holes out in the universe, including masses and spins that offered clues to how those black holes formed. By 2020, the LIGO-Virgo network had even picked up signals from mixed pairs, collisions between a black hole and a neutron star, demonstrating that all manner of cosmic smash-ups can be heard. Through these gravitational wave listens, we began to catalogue an otherwise invisible realm of the cosmos and learn about phenomena we previously only theorized about. Then came August 17th, 2017, a date that marked the dawn of multi-messenger astronomy. On that day, LIGO and Virgo observed a new kind of gravitational wave signal, one that lasted nearly a minute and had a different pattern, chirp, than the black hole mergers. It was the signature of 2 neutron stars spiraling together and merging. This time, unlike the mostly silent black hole collisions, the neutron star merger produced a brilliant flash of electromagnetic radiation. Just about 2 seconds after LIGO-Virgo recorded the gravitational waves, NASA's Fermi satellite detected a short gamma-ray burst from the same region of sky. Alerted by these signals, astronomers around the world swung their telescopes to that patch of sky in search of a glow. Within hours, they found a new point of light in a galaxy about 130 million light-years away. Over the next days and weeks, this transient object, dubbed a kilonova, brightened and then faded, its light changing from bluish to reddish. Spectra of the kilonova's light revealed the presence of newly forged heavy elements. In that one event, labelled GW 170817, we witnessed both gravitational waves and electromagnetic waves from the same source. The gravitational waves told us 2 neutron stars, each about 1.4 times the Sun's mass, had collided. The gamma rays and visible infrared light revealed the fiery aftermath, including the creation of elements like gold and platinum. This event marked the dawn of multi-messenger astronomy. For the first time, we observed a cosmic catastrophe through both ears and eyes, hearing the space-time ripples of the merger and seeing the glow of the debris. It confirmed that neutron-star collisions are a source of heavy elements, answering a long-standing question of where elements like gold are made. And it dramatically illustrated the power of combining gravitational wave data with traditional astronomy. We had observed a single event with two completely different messengers, enriching our understanding far beyond what either alone could provide. Gravitational wave astronomy was now a reality. What had been a thought experiment in Einstein's mind became a practical observational science. With every new detection, we peel back another layer of the previously invisible universe. We have started to map the hidden lives of black holes and probe the extreme physics of neutron-star collisions. And we are just at the beginning. As detector sensitivities improve and new observatories join the network, we may one day hear the faint murmurs of supernova core collapses, or the rumble of primordial gravitational waves from the very dawn of time. Plans are already underway for more advanced gravitational wave detectors on Earth, with names like Cosmic Explorer and the Einstein Telescope, and for a space-based detector called LISA, Laser Interferometer Space Antenna, in the 2030s. These future instruments will tune in to lower-frequency gravitational waves, allowing us to detect collisions of supermassive black holes in distant galaxies, and perhaps even vibrations left over from the Big Bang itself. Our journey through the cosmos so far has shown us a universe richer and more surprising than we ever imagined. We have discovered that the cosmos is vast and filled with galaxies upon galaxies. We have seen that it is dynamic, expanding and evolving from a hot primordial state. We have detected the whispers of the Big Bang in microwaves, uncovered unseen dark matter shaping cosmic structure, and found a mysterious dark energy accelerating the expansion. We have watched stars live and die in spectacular ways, and realized that in their death they sow the seeds of new stars, planets, and even life. We have found planets around other suns by the thousands, some of which may be Earth-like, raising anew the question of life beyond our world. And we have opened our ears to the music of spacetime, catching the ripples of massive bodies colliding in the dark. Yet, the exploration is far from over. With each answer, new questions arise. As we venture onward, the cosmos continues to reveal new mysteries and wonders, beckoning us to delve deeper. With calm curiosity and a sense of awe, we continue our journey, ready to discover even more in the chapters of cosmic history yet to come. Far beyond the reach of any human hand, a golden eye floats in the darkness. The James Webb Space Telescope, with its 18 shimmering hexagonal mirrors, has opened a new window on the universe. It drifts at a quiet point in space, 1,000,000 miles from Earth, shielded from the sun by a broad, silvery sunshade. In this cold and silent vigil, Webb gazes deeper into the cosmos than we have ever seen, sensitive to the faint infrared glow of creation's first lights. Through these next-generation eyes, humanity is peering farther back in time than ever before, witnessing cosmic dawns that occurred billions of years ago. In a single image from Webb's gaze, thousands of distant galaxies speckle the canvas of space, some so far away that their light began its journey not long after the Big Bang. Webb's infrared vision pierces clouds of cosmic dust that once hid newborn stars, now revealing stellar nurseries where new suns ignite. Ancient galaxies, blurred by time and distance, sharpen into view, their shapes and structures whispering secrets about how the first star cities grew when the cosmos was young. Each observation by this telescope brings a sense of quiet awe, as if we are eavesdropping on creation itself, watching the first chapters of an infinite story unfold across the sky. This observatory's gaze is not only fixed on the distant past, it's also revealing wonders closer to home. Webb has turned its eye to exoplanets, planets orbiting other suns, and begun to read the faint signatures of molecules in their atmospheres. By watching a planet drift across the face of its star, it can detect tiny color shifts in the starlight caused by the planet's air. In this way, Webb has found clues of water vapor wafting through alien skies and traces of familiar gases like carbon dioxide on distant worlds we cannot yet visit. It is as though we've learned to sense the breath of these far-off planets, searching for anything that might hint at the presence of life. These breakthroughs are only the beginning. Each passing month, Webb delivers new images and spectra that deepen our understanding. Star-forming nebulas, sculpted by stellar winds and radiation, shimmering rings of dust around young suns, hinting at planets coalescing within, even the dim glow of lonely brown dwarfs wandering in the dark. In a short time, this golden-eyed telescope has immeasurably enriched our cosmic perspective. On Earth, we are building more eyes to join Webb in exploring the heavens, high atop remote mountain peaks, where the air is thin and clear. Enormous observatories are rising. In Chile's Atacama Desert, a colossal dome now houses what will soon be the largest optical telescope in history. The extremely large telescope's mirror, nearly 40 meters across, dwarfs all its predecessors. It is composed of hundreds of precision-crafted segments fitted together into one gigantic, light-collecting eye. Not far away, the giant Magellan telescope is under assembly, with 7 enormous mirrors working in unison as a single instrument, each mirror so large that a person could lie across it comfortably. These behemoths, and others of similar ambition, represent the next generation of ground-based astronomy. When they open their eyes on the universe, they will gather the faintest light from the most distant objects, the first stars that ever twinkled, the subtle gleam of Earth-like planets orbiting nearby stars. What is today barely a smudge of light may soon transform into a rich landscape of detail under their gaze. To achieve such sharp vision, these observatories employ ingenious techniques. Even on the best nights, Earth's atmosphere shimmers and blurs the starlight. But the new telescopes will fight this blur with adaptive optics. By shining lasers into the sky to create artificial guide stars, and using flexible mirrors that adjust in real time, they will cancel out much of the atmosphere's distortion. The result is clarity nearly as crisp as the view from space. With this advance, a ground telescope can resolve features once thought possible only for instruments in orbit. Astronomers dream that with such clarity, the largest telescopes might directly capture images of exoplanets, perhaps tiny pinpricks of light next to their brilliant stars, and analyze those faint glows for signs of clouds, oceans, or even vegetation on distant worlds. The same instruments will dissect the light of faraway galaxies, mapping the distribution of mysterious dark matter and measuring the universe's expansion with unprecedented precision. Our improved eyes are not limited to visible light or infrared. Across the spectrum and beyond, we are extending our senses. In radio waves, arrays of antennae spread across continents act together as one enormous ear pressed to the cosmos. Soon, the square-kilometre array, a vast network of dishes and antennas in distant deserts, will tune in to the faint murmur of hydrogen gas from the epoch when the first galaxies were assembling. It will catch fast radio bursts that flicker like cosmic whispers from unknown sources, and listen for the static of the Big Bang's afterglow rippling through space. In orbit, X-ray observatories keep watch on high-energy flashes, capturing rays emitted by matter spiraling into black holes or by titanic collisions of neutron stars. These energetic beacons reveal a violent side of the universe invisible to our eyes, showing us the fireworks of supernova remnants and the searing cores of galaxies where supermassive black holes lurk. We have even begun to detect the universe without using light at all. Sensitive instruments like LIGO have felt the subtle tremors of spacetime itself, gravitational waves, washing over Earth from distant cataclysms. These tiny ripples, caused by events like black holes merging billions of light-years away, jostle our detectors ever so slightly, announcing occurrences we could never perceive with traditional telescopes. Each new way of sensing the cosmos, be it radio, X-ray, particle, or gravity wave, adds a layer to our understanding. Together, they transform the silent darkness into a rich symphony of information, allowing us to experience the universe with multiple senses. Standing at the dawn of these new capabilities, we can only wonder what revelations await. As our telescopes and detectors grow more powerful, they may finally answer questions that have lingered for generations. How did the first stars ignite after the cosmic dark ages? And what were they like? Is our solar system rare or common in its ability to support life? Or are planets teeming with life scattered throughout the galaxy? What exactly are dark matter and dark energy? Those unseen influences that shape galaxies and drive the universe's acceleration. Our next generation eyes are poised to probe these mysteries. They might find truly Earth-like planets in the habitable zones of distant suns, their atmospheres carrying the faint chemical fingerprints of life. They could witness one of the first supernovae that ever exploded, an ancient star's death lighting up the young universe and seeding space with heavy elements needed for planets and people. They might even stumble upon phenomena so unexpected that we have no name for them yet, upending our models and sparking new questions. Each time humanity has built a better way to see the cosmos, we have been astonished by what we found. Now, as we deploy the most advanced observatories in history, a quiet, hopeful excitement stirs. We sense that we are on the verge of more humbling and awe-inspiring discoveries. And while these grand instruments gaze into the distance and the deep past, we remember that exploration isn't only about observing from afar. To truly know, sometimes we must go and touch. Even as our telescopes watch the far frontiers of space and time, we are also sending intrepid scouts into the nearer darkness, to visit the worlds that share our sun. Our journey continues with those voyages, as we step from observation to action, from distant vision to up-close exploration of new horizons. On a cold Martian afternoon, a lone rover trundles across rust-coloured sands under a butterscotch sky. This is Perseverance, NASA's robotic explorer, traversing the floor of Jezero crater, where a river delta once fanned out into a lake. Long ago, water carved sinuous channels into these crater walls and left behind clay-rich sediments, the kind of environment that on Earth teems with life. Today, Jezero is dry and silent. Perseverance's wheels crunch over ground that hasn't felt rain in billions of years. Yet hidden in the rocks and dust could be chemical fossils or traces of ancient microbes, remnants of a time when Mars was warmer and wetter. The rover pauses at rocky outcrops, drilling into their sun-baked layers and extracting cylindrical cores of stone. Each sample is sealed in a small tube, little time capsules of Martian history, and set aside on the surface, awaiting a future mission that will whisk them back to Earth. As Perseverance works, it occasionally stops to listen to the whisper of the Martian wind, or to watch dust devils dancing on the distant plains. Each day's drive is careful and deliberate, the rover's cameras scanning for unusual textures or glints, a hint of carbonate minerals that might signal ancient water chemistry, or a pattern in rock that resembles microbial mats seen in Earth's own fossil record. In its patient exploration, Perseverance serves as our eyes, ears, and hands on Mars. A diligent geologist and astrobiologist rolled into one, searching for answers in the silent stones of an alien world. High above the rover, a tiny helicopter named Ingenuity springs to life. With a soft whir, it lifts off into Mars's thin air, the first powered flight ever made on another planet. Its rotors blur nearly silently in the frail atmosphere, achieving what once seemed impossible. Ingenuity soars a few dozen feet up, scouting ahead for Perseverance. It photographs the terrain from above, mapping safe paths and interesting targets. Each brief hop is a new Wright brothers moment on a distant world, a testament to human creativity and the desire to push boundaries. The little helicopter's shadow skims over ochre ridges and ancient stream beds as it darts across the landscape. Together, the rover and its flying companion form a pioneering duo, one slowly rolling on the ground, the other flitting through the sky, expanding the ways we explore other planets. Their presence makes Mars feel more tangible, no longer just a distant point of light, but a place where we have footprints, or rather wheel tracks, and airborne trails. When the sun sets and the temperature plunges, Perseverance hunkers down for the frigid night, and Ingenuity rests as well, awaiting another dawn. Scattered nearby, a handful of sealed sample tubes lie patiently in the dust, filled with pieces of Mars that may contain answers to one of humanity's oldest questions. Did life ever arise beyond Earth? Mars is just one chapter in our journey to new worlds. Farther from the Sun, beyond the asteroid belt, lie the giant planets and their moons, a realm of deep cold and surprising wonders. Around ringed Saturn, the Cassini spacecraft spent 13 years unveiling a carnival of marvels. Among its revelations was a tiny moon named Enceladus, an ice-covered globe that astonished scientists by spraying geysers into space. When Cassini first spotted the plumes jetting from Enceladus's south pole, it saw fine curtains of ice particles and vapor venting from long fractures in the moon's crust, nicknamed tiger stripes. This small moon, only about 500 kilometers across, harbors a liquid water ocean beneath its frozen shell, kept warm by tidal forces flexing its interior. Cassini dared to fly directly through those geysers, and in doing so, essentially tasted the moon's hidden sea. The spacecraft discovered salty water, rich in simple organic molecules, along with tiny grains of silica that hinted at hot mineral springs on a seafloor. It was a stunning discovery. All three key ingredients for life as we know it, liquid water, organic chemistry, and an energy source, appear to be present on Enceladus. In the dark ocean beneath its icy crust, warmed by what might be hydrothermal vents, could primitive life forms be swimming, entirely cut off from sunlight, yet thriving around warm undersea springs? We don't yet know, but Enceladus vaulted into the spotlight as one of the most promising places to search for life beyond Earth. This little moon taught us that even in the far reaches of the solar system, where sunlight is feeble, habitable environments might persist in the unlikeliest of places, waiting to be discovered. Jupiter's moons have similarly beckoned us, especially Europa, a world slightly smaller than our moon, but with an outsized reputation in the quest for life. Europa's surface is a bright shell of ice crisscrossed by dark, rust-coloured streaks and ridges. It looks as if someone took a white cue ball and cracked it, then filled the cracks with reddish-brown dye. That fractured surface speaks of a restless interior. Beneath Europa's ice, almost certainly, lies a global ocean of liquid water, kept unfrozen by the gentle kneading of Jupiter's gravity. This notion first gained traction when the Voyager and Galileo probes observed Europa's relatively smooth surface, indicating it is geologically young, and detected a magnetic disturbance around Europa, hinting at a conductive fluid, likely a salty ocean, beneath the ice. Europa's ice might be tens of kilometers thick, but in some regions it could be thinner, possibly even allowing water to occasionally erupt through, similar to Enceladus's plumes. Indeed, the Hubble Space Telescope has caught tantalizing signs of water vapor above Europa, suggesting that this ocean might be venting into space through cracks. If that's happening, we could potentially sample Europa's ocean indirectly, just as we did Enceladus's, by flying a probe through the plumes to sniff out any complex molecules or maybe even biological material. To probe these mysteries, NASA is preparing the Europa Clipper mission. When it arrives in the early 2030s, it will perform dozens of flybys of Europa, mapping the ice, measuring the moon's gravitational and magnetic fields to confirm the ocean's depth and salinity, and scanning the surface for chemicals or warm spots where the ocean might be closest. The main goal is to assess Europa's habitability, to gather enough evidence to answer, could life find a foothold here? We imagine Europa's hidden ocean with a sense of wonder, a boundless, pitch-black sea, perhaps 100 kilometers deep, teeming with possibilities. Maybe it has hydrothermal vents, like Earth's oceans do, complete with nutrient-rich mineral soups. Could simple organisms cluster around those warm vents, as they do on Earth's ocean floor? It's a thrilling thought that an ecosystem might be thriving right now in the dark, under an alien ice sheet. Europa Clipper won't be able to answer that definitively, but it will bring us much closer. And in the future, perhaps a dedicated lander will touch down on Europa's frozen plains, drill or melt through the ice, and send a submersible robot into the black waters to search for living creatures in that alien abyss. Yet another destination entices us with a wholly different kind of environment. Titan, Saturn's largest moon. Titan is often described as a cousin of Earth in deep freeze. It has a thick atmosphere, so thick and hazy that it shrouds the entire surface in a permanent orange twilight. For a long time, this haze kept Titan's secrets well hidden. But in 2005, humanity's curiosity literally touched down. The Huygens probe, carried to Saturn by Cassini, parachuted through Titan's atmosphere and landed on its strange surface. As Huygens descended, it sent back pictures of a rust-coloured sky, and astonishingly, glimpses of what looked like river channels and shorelines below. When it finally came to rest, it provided the first ground-level view of Titan. A bleak, dim landscape with a pebble-strewn surface. Those pebbles were made of water ice, as hard as rock in the extreme cold, and the soil was damp with hydrocarbons. Titan, we learned, has lakes and seas, not of water, but of liquid methane and ethane. At its poles, vast lakes and small seas dot the landscape. We've even seen evidence of rainstorms in Titan's weather. It is the only other world in the solar system, aside from Earth, known to have stable liquid on its surface. The entire hydrological cycle on Titan is conducted with methane. It evaporates, forms clouds, rains down, and fills lakes, only to evaporate again. This exotic meteorology has carved features startlingly reminiscent of Earth's. River deltas, lake shorelines, even broad sand dunes near the equator sculpted by the wind. Titan's chemistry, however, is something truly unique. Its atmosphere, mostly nitrogen like Earth's, has a significant amount of methane and is stirred by sunlight and Saturn's magnetic field to produce a wealth of complex organic molecules. These organics drift down out of the sky like a fine soot, accumulating in Titan's soil and possibly enriching its lakes with compounds that on Earth would be the building blocks of life. In Titan's frigid conditions, around 180 degrees C on the surface, water is rock solid, and life as we know it, which requires liquid water, seems unlikely. But some scientists wonder, could life find a way with liquid methane as a solvent? If so, it would be a form of life very different from our own, with biochemistry perhaps based on entirely distinct principles. Titan pushes us to broaden our concept of habitability. To investigate Titan's potential and understand its chemistry better, NASA is sending the Dragonfly mission. In the mid-2030s, if all goes well, a robotic rotorcraft the size of a large drone will arrive at Titan. Because Titan's gravity is weak and its atmosphere dense, flying there is comparatively easy. Dragonfly will be able to soar from site to site, exploring dozens of kilometers apart, something a rover could never do in a reasonable time. It will land first among Titan's equatorial dunes, analyzing the dark, organic-rich sands. Later, it will hop to other interesting locales, perhaps an impact crater where past heat might have briefly melted water ice and mixed it with organics, creating a chemical playground for prebiotic reactions. At each stop, Dragonfly's instruments will sniff the air, scoop the soil, and examine the chemistry. It will look for patterns like those that life might produce, maybe slight preferences for certain molecular structures or unusual ratios of isotopes. It will also monitor Titan's weather on the ground, listening to the wind and watching for the glint of sunlight off distant methane lakes. Through Dragonfly, we will for the first time roam the skies of a moon beyond our own, bringing a new level of intimacy to our study of the outer solar system. All these far-flung missions, rovers on Mars, orbiters and landers at icy moons, flying probes on Titan, are united by a common quest: to find evidence that we are not alone, or at least to understand whether other environments can nurture life. They form a modern odyssey of exploration, fueled by curiosity and a profound longing to know if life's spark has flared elsewhere in our solar system. So far, each world has kept its secrets. Mars has teased us with plumes of methane gas that come and go with the seasons. Methane can be a byproduct of microbial life, but also of geology, and with ancient organics locked in rocks. Intriguing, but not proof of life. Enceladus gave us complex organic molecules in its plumes, but no definitive sign of biology. Europa's invitation lies ahead. Titan's verdict remains open. It might be that life is exceedingly rare, and these worlds, though once potentially habitable, never actually hosted living organisms. Or it could be that life, if present, exists at levels or depths we haven't yet been able to detect. The silence so far only heightens the suspense. Our search is far from over. In truth, it's just beginning in earnest. In the coming years, we plan to bring Mars right into our laboratories by fetching those samples that Perseverance is collecting. With Martian rocks and soil in hand on Earth, scientists will scrutinize them for microfossils or chemical traces that only living processes produce. A future mission to Enceladus might orbit that moon and fly repeatedly through its geysers, effectively tasting the ocean over and over for signs of bacteria or amino acids. Europa Clipper will map out whether Europa is venting any of its ocean contents. And one day, perhaps a Europa lander could drill a meter or two into the ice to find any clues just beneath the blasted surface. Dragonfly's findings on Titan will inform us if complex chemistry there has taken any steps toward life's threshold. We are also considering more audacious ideas. Maybe a spacecraft could one day sail the hydrocarbon seas of Titan, or a submarine could dive into them. Perhaps a future probe might even attempt to melt through on Europa's ice, or a hovercraft sampling of the denser plumes of Enceladus with more advanced life detection equipment. As our robotic envoys beam back their treasure troves of data, they transform these distant orbs from mere points of light into richly characterized worlds. We can imagine standing on them, watching a pale salmon sunset from Mars's dusty horizon, or looking up from Europa's stark surface to see Jupiter filling the sky with its banded majesty. We can picture Titan's orange skies and dim daytime, perhaps standing by a methane lake with Saturn's faint light glimmering through the haze. These mental images forge a connection between us and these remote places. They remind us that even though these worlds are inhospitable by earthly standards, they are real places with landscapes and weather and histories of their own. They have become extensions of our geographical understanding, part of the ever-expanding map of where we have been, if not in person, then through our robotic pioneers. Each world we explore teaches us more about what's necessary for life and how unique or common Earth might be. By studying Mars, we learned that a planet can go from wet to dry on a global scale. By probing ocean moons, we see that liquid water can exist in the freezing outer solar system if there's enough tidal energy. By examining Titan, we realize that even without liquid water, interesting chemistry abounds under an umbrella of atmosphere. We are, in a sense, assembling a jigsaw puzzle of habitability. We don't yet know what the final picture will be: widespread life, rare life, or life only on Earth. But piece by piece, the image is becoming clearer. It's humbling either way. If we do find that life independently arose on Mars, or Enceladus, or elsewhere nearby, it would suggest life might be common in the universe, that wherever conditions are right, biology sparks and evolves. That would make the night sky feel a little less lonely, as each star could harbour not just planets, but living ecosystems of some kind. On the other hand, if we search diligently and find nothing, that sharpens the miracle of our own existence. It could mean that a long chain of flukes made Earth a cradle of life, and that we might be one of very few, or even the only, living worlds in our cosmic neighbourhood. In that case, our responsibility to cherish and protect life here becomes even greater, as it could be a truly rare and precious phenomenon. Either outcome, a universe teeming with life, or one in which life is vanishingly rare, profoundly affects our perspective. And interestingly, either outcome is something to marvel at. A cosmos filled with life would be glorious to discover. A cosmos in which life is a tiny spark in the dark is poignant and urges us to be good stewards of that spark. So, as our explorers roam Mars's craters and dive through icy plumes, we hold our breath for whatever news they bring. Each drill sample and each vapor sniff could, in theory, be the one that finally answers us with evidence of life beyond Earth. Until then, we continue in hope and with patience. As our mechanical scouts push ever outward, they also pave the way for something even more daring, the day when human explorers might join them. The robots are trailblazers, gathering knowledge and confidence for the moment we decide to send flesh and blood people to tread the red sands of Mars or the icy plains of a moon. The quests on Mars, Europa, Enceladus, and Titan are building experience in living off the land, in operating far from Earth, in designing instruments to detect life. All of these will feed into humanity's grander odyssey beyond Earth, one that is already beginning to unfold. Even as we scour our solar system for signs of life, our gaze extends further outwards, to the planets orbiting other stars. The past few decades have revealed a startling truth. Planets are everywhere. The night sky, once thought to be populated only by stars, is now understood to be filled with worlds. Almost every star twinkling above has a family of planets around it. The cosmos has become a garden of planets, some scalding hot, hugging too close to their suns, some icy and dark, far from the warmth, some huge gas giants with raging storms, and some, possibly, small rocky spheres with liquid water and gentle climates. We have detected more than 5,000 exoplanets, and the number grows every month. Among them are some that tantalizingly resemble our own world, at least in size and orbit. We've found planets roughly Earth-sized orbiting in the habitable zone of their stars, that Goldilocks region where temperatures might allow liquid water on the surface. The discovery of these alien worlds has transformed our view of the universe. It feels more intimate now, as if the distant stars have neighborhoods, not unlike our own. One of the most celebrated of these discoveries is the TRAPPIST-1 system, around a faint, cool red dwarf star, only 40 light-years away. 7 Earth-sized planets circle in a tight configuration. Remarkably, 3 of these worlds lie in the star's habitable zone. The entire system is so compact that all 7 planets would fit comfortably within Mercury's orbit around our Sun. To an observer on one TRAPPIST-1 planet, the other planets could appear as sizable disks in the sky, some potentially showing phases like our Moon. It's easy to let the imagination roam. Standing on the surface of one of these worlds, under a dim, salmon-coloured sky, for the star is much cooler and redder than our Sun, you might see another Earth-sized planet looming on the horizon, close enough to make out cloud patterns if it has any. It's a scenario straight from science fiction, yet rooted in scientific discovery. We don't know if these planets have atmospheres or water, but we know they exist in a configuration that would allow those things. And if conditions turned out to be right, who knows? Maybe life has had a chance there as well. With each new planetary system found, our cosmic loneliness is just a bit alleviated. Knowing that planets abound means the stage is set for life almost everywhere, even if the actors have yet to be discovered. But how can we find out if any of those distant worlds are alive? We can't, not yet anyway, send probes across tens or hundreds of light years, nor can we see their surfaces directly with current technology. Instead, scientists have become cosmic detectives, finding subtle clues in the faint light that reaches us across space. The primary way we study exoplanets is through their effects on their parent star's light. When a planet transits, that is, passes in front of its star from our perspective, it causes a tiny dimming of the star's light. That dip tells us the planet's size, and from the timing we deduce its orbit, and thus roughly its temperature environment. Beyond that, something magical happens. As the planet transits, a little starlight filters through its atmosphere, if it has one, on the way to us. The gases in that atmosphere imprint their unique signatures on the starlight. Certain colours get absorbed by certain molecules. By splitting the star's light into a spectrum, like a rainbow, and analysing it during the transit, we can see the fingerprints of those gases. This technique, called transmission spectroscopy, has already borne fruit. It's most effective for big planets around small stars, for example, hot Jupiter-like planets that cause significant dimming and have bloated atmospheres. Using the Hubble Space Telescope and others, astronomers detected sodium gas in a distant planet's sky back in the early 2000s. Since then, we've identified water vapor on several exoplanets, often large ones, and even clouds made of exotic substances like vaporized rock or glass. astonishing rains of iron on some ultra-hot worlds where temperatures soar above 2,000 degrees. These findings sound fantastical, but underscore that we are starting to probe the weather on worlds light years away. With the arrival of the James Webb Space Telescope, our reach has extended further. Webb's instruments have, for instance, clearly picked out the signature of carbon dioxide in the air of a planet about 700 light-years from here, the first unambiguous detection of that gas in an exoplanet atmosphere. Webb has also detected hints of other interesting molecules, like possible clouds and haze on a few smaller exoplanets, and even a tentative sign of chemical compounds that, on Earth, are linked to life, though it's very early and unconfirmed. The ultimate hope is to find what we call a biosignature, a combination of characteristics that strongly suggests life's presence. On Earth, the prime example is our oxygen-rich atmosphere. Oxygen is highly reactive. Without life constantly producing it via photosynthesis, it would quickly bind with rocks or animals or fire and vanish. Yet we have 21% oxygen in our air, thanks to billions of years of plant and algal activity. Moreover, our atmosphere has methane too, a gas that reacts with oxygen and would not linger unless something kept emitting it, from both biological and some geological sources. The simultaneous presence of lots of oxygen and some methane in an atmosphere is hard to explain without invoking life. There are other potential biosignatures. For instance, certain ratios of isotopes in the air, or the presence of compounds like nitrous oxide, or even industrial pollutants that could indicate technological civilizations. Another intriguing possibility is the red edge. On Earth, vegetation strongly absorbs red light for photosynthesis and reflects infrared, so a planet covered in plants might show a telltale bump in its reflectance spectrum at a particular wavelength. Detecting something like that on an exoplanet would be like seeing the spectral shadow of a forest. It must be said that interpreting biosignatures will be tricky. Planetary environments are diverse, and non-biological processes can sometimes mimic the signs of life. For example, a planet with an ocean and lots of volcanoes could potentially accumulate oxygen from water vapor being split by sunlight, even if no life existed. Methane can arise from geothermal sources. Unusual atmospheric chemistry might arise from a recent impact or a planet being slowly vaporized by its star. So, scientists are cautious. They often say we'll need multiple lines of evidence. Perhaps we find a planet with an Earth-like average temperature, and we detect oxygen and some methane, and also see the glint of possible oceans and maybe seasonal changes in gas amounts. Altogether, that would be a compelling case that something is alive there. Already, hints and debates have begun. Not long ago, Webb studied a planet in the habitable zone of a cool dwarf star, the planet K2-18b, and found methane and carbon dioxide in its atmosphere, and even a tentative indication of a molecule that on Earth is associated with living organisms. This caused a stir. Could we be seeing the first faint evidence of alien life chemistry? The result is far from confirmed and could turn out to have a non-biological explanation. The planet is more like a mini Neptune with a deep ocean under a hydrogen sky, conditions very different from Earth. Still, just reaching the point of detecting such molecules is a remarkable achievement and a proof of concept that we can sniff out the compositions of smaller, temperate exoplanets. Closer to home, a contentious discovery was the report of phosphine in the clouds of Venus, a gas that on Earth is produced by microbes in oxygen-free environments. Venus is incredibly harsh, with sulfuric acid clouds and high heat. So the idea of life there was surprising, and many scientists are skeptical or have proposed other phosphine sources. The Venus story remains unresolved. illustrating how careful we must be in claiming a biosignature detection. We may face a similar situation with exoplanets. The first evidence of life might be ambiguous and hotly debated for years. To better our chances of finding clear evidence, new tools are on the drawing board. One idea is a future space telescope specifically designed to image Earth-like exoplanets. This is extremely challenging because an Earth analog is so faint and so close to its bright star. But there are approaches to overcome that glare. One is to equip a telescope with a coronagraph, an internal mask that blocks the star's light, allowing any planets nearby to pop out in the image. Another concept is the star shade, a giant, flower-shaped screen, tens of thousands of kilometers in front of a space telescope, aligning perfectly to cover the star, casting a shadow so the telescope sees just the planetary system lit around it. With these methods, scientists hope to directly image small planets and obtain their spectra, revealing details like whether they have oceans and continents, different surfaces reflect differently, or clouds in their atmospheres. The upcoming generation of extremely large ground telescopes will also try to directly image large terrestrial planets around the nearest stars using advanced optics. It's possible that in a decade or two, we'll have the capability to detect an Earth-like planet around a Sun-like star and analyze a bit of its light. If that day comes, and we see, for instance, a combination of oxygen, water vapor, and perhaps a whiff of something like chlorophyll's signature, or a weird imbalance of gases that screams life at work, it will arguably be one of the most profound moments in scientific history. The search for life in the universe isn't confined to chemistry and telescopes. There's also the ongoing attempt to pick up signals from intelligent life. For over half a century, SETI researchers have aimed radio receivers at nearby stars, seeking the unmistakable hallmarks of engineered communication. Perhaps a steady, narrow-band whistle that nature doesn't produce. So far, no confirmed extraterrestrial broadcast has been heard. There have been intriguing blips. The famous WOW signal in 1977 was a strong, unexplained signal that appeared once and never again, leaving us wondering. We've also had public excitement over things like a strange dimming star, nicknamed Tabby's star, where one outlandish hypothesis was a gigantic alien megastructure causing the dips in light. Subsequent studies pointed toward dust as the cause of the dimming, not colossal engineering projects. And fast radio bursts, extremely brief, distant flashes of radio waves, were once speculated by a few to be possible beacon signals, but they're now largely thought to be natural, perhaps from neutron stars. While the idea of contacting or detecting another civilization fires the imagination, it remains an unanswered question. The silence could mean intelligent life is exceedingly rare, or simply that we haven't been listening the right way, or long enough. It's a question that keeps us looking up, and occasionally aiming an ear to the sky, just in case someone, somewhere, is saying hello. In all likelihood, the first sign of life out there, if it comes, will be in the subtle chemistry of an exoplanet's atmosphere, rather than a clear message from an alien mind. And when we get that first hint, we'll have to be patient and meticulous to verify it. Yet consider how momentous it would be. It would mean that life is not unique to Earth, that the spark of biology has lit up elsewhere, even if only in humble, single-celled form. It would suggest the universe is fertile ground, that under the right conditions, life will emerge, making the cosmos a more welcoming, lively place than the sterile void it could otherwise appear. Conversely, if after examining many Earth-like planets, we find none with telltale biosignatures, that would underscore how special our planet is. A solitary oasis in a vast, perhaps mostly barren sea. Either discovery would reshape our understanding of our place in the cosmos. For now, we inch toward that discovery with each technological advance. We stand at an extraordinary moment. For the first time in human history, the question, "Are we alone?" is one we have some real hope of answering scientifically in the foreseeable future. It's no longer merely a philosophical musing or a topic for speculation. It's a research program, with data coming in, with hypotheses being tested. We can be sure the universe will not give up its secrets easily. There will be false alarms and frustrations. We might need the next generation of telescopes, or the next after that, to get a clear answer. But we are on the path, and as long as our civilization continues to value knowledge and exploration, we will keep going. Even as we extend our search for life and grapple with cosmic questions of biology, we find ourselves drawn to puzzles that lie at the very edge of understanding, questions about the universe taken as a whole. We've peered into the vastness and seen the grandeur of countless galaxies. We've also peered into the subatomic world and seen nature's tiniest building blocks. Now we yearn to connect the dots, to understand how the universe began, why it has the features it does, what its fate will be, and whether our reality is the only reality. These are the theoretical frontiers, where physics meets philosophy in many ways, and where answers remain elusive, but endlessly fascinating. What if our universe is not alone? The concept of a multiverse has entered both scientific discourse and popular imagination. It posits that our universe, the sum total of all we can observe, from quarks to galaxies, might be just one bubble in an infinitely larger froth of universes. How could such a thing be? One motivation comes from the theory of cosmic inflation, which suggests that a tiny fraction of a second after the Big Bang, our universe underwent a stupendously rapid expansion. It's like a balloon inflating to astronomical size in an instant. If inflation happened here, perhaps it happened elsewhere, and perhaps it never completely stopped. In some theories, the inflationary expansion of space goes on eternally in various regions, continually spawning new bubble universes with their own big bangs. Our universe would just be one bubble where inflation stopped and stars and galaxies formed, while elsewhere, other bubbles are being born or evolving on their own paths. These other universes could have different physical laws or constants. Imagine one where gravity is stronger, or where there are 5 dimensions, or where no stable atoms ever formed. They would be separated from us, essentially forever unreachable, their light, if any, unable to bridge the gulfs of inflating space between us. It's a strange, almost transcendental idea, but it comes out of serious mathematics and attempts to understand why our universe's parameters are so finely tuned for life. Some scientists have even looked for evidence of other universes in our own. For example, a collision between our universe and another early on might have left a subtle pattern in the cosmic microwave background, the afterglow of our Big Bang. So far, no telltale sign has been seen, but the possibility remains open, whispering that reality might be much larger and more varied than we ever thought. Another kind of multiverse emerges from quantum theory. In quantum physics, particles exist in a haze of probability. They can be in multiple states at once until observed. One interpretation of this, the many worlds interpretation, suggests that every time a quantum event has multiple outcomes, all outcomes occur, each in its own branch of reality. In one branch, an atom decays. In another, it doesn't. In one branch, you took a left turn. In another, you went right. These branches would constitute parallel universes, continually splitting off from each other, each as real as the other, but non-communicating. If that sounds like science fiction or philosophy, it largely is at this point. It's a way to interpret quantum mechanics without requiring a single outcome. It means that the universe constantly forks into innumerable copies. Whether this is really happening is hotly debated. It's a very radical idea with no empirical test currently. Yet it shows how our attempts to understand the quantum world can challenge our sense of a single, solid reality. Moving from the speculative multiverse to our known universe's origin, we confront the moment of the Big Bang. Our theories and observations can describe the universe back to a tiny fraction of a second after the Big Bang. But as we approach time zero, things get murky. At extremely high energies and densities, our two foundational theories, quantum mechanics and general relativity, are both needed, and they conflict with each other. We lack a complete theory of quantum gravity to handle those conditions. Quantum cosmology is the field that attempts to marry the physics of the very small with the entire universe. Some proposals suggest that the universe in its earliest instant can be described as a quantum wave function, a kind of fuzzy state where space and time as we know them didn't yet exist in a classical sense. In this view, time might have been an emergent property that came into being as the universe decided on a particular state. It's a bit like asking what's north of the North Pole. Maybe the question of what happened before the Big Bang is simply meaningless, because time itself began with the Big Bang. But not all theories cut off time like that. Others, like certain versions of string theory or loop quantum gravity, allow for a pre-Big Bang scenario. There could have been a prior universe that contracted, leading to a bounce that became our Big Bang, in which case time is a cyclical loop, and perhaps the death of one universe seeds the birth of another, eternally. We don't have evidence for this, but it's a beautiful possibility, that the Big Bang was not an ultimate beginning, but a transition. These questions about multiple universes and the beginning of it all often lead naturally to the question of the ultimate fate of the cosmos. Will it expand forever? End in fire or ice? As recently as the 1990s, astronomers were considering two main scenarios: an open universe that expands forever, slowly cooling and fading, or a closed universe where gravity eventually halts the expansion and pulls everything back into a fiery, big crunch. The discovery of the universe's accelerating expansion, attributed to something we call dark energy, tipped the scales toward endless expansion. If dark energy continues to behave as it does now, like a constant energy embedded in space itself, our universe will keep expanding faster and faster. Distant galaxies will recede until they disappear from view, their light stretched beyond detection. The night sky over tens of billions of years will gradually lose its stars as they wink out or cruise beyond the horizon of visibility. Trillions of years hence, new stars will no longer form because the raw material, gas, will be used up or too dispersed. The last stars, faint red dwarfs that burn their fuel ever so slowly, might shine for trillions more years, but one by one, they too will extinguish. Planets that once basked in warmth will find themselves orbiting cold, dark remnants, white dwarfs, neutron stars, black holes. Collisions may occasionally spark a brief light as objects merge, but as eons pass, those events will dwindle. In some far future, perhaps 1,000 years from now, a 1 followed by 100 zeros, even the gargantuan black holes at the centers of galaxies will evaporate via Hawking radiation, each ending in a final whisper of light. At that point, the universe would be effectively dark and silent, filled with a thin haze of particles and photons stretched to such long wavelengths they barely interact with anything. This is the big freeze or heat death scenario, A cosmos faded to black, activity nearly ceased, approaching a state of maximum entropy where no work can be done. It's a rather melancholy picture of the end. Not a bang, but an ever-dimming fizzle into nothingness. Yet, it is so far in the future that it almost becomes abstract, so far removed from any human timescale that it's like contemplating the death of an ocean, one drop at a time. There are alternative fates that have been theorized. If dark energy were to somehow grow in strength, in some models called phantom energy, it could lead to a catastrophic big rip. In that scenario, billions of years from now, dark energy's repulsive force would increase so much that it overcomes all other forces. First, galaxies would be torn apart, then solar systems would unbind, then planets and stars would be shredded, and ultimately, even atoms could be rent asunder, all in the final moments as the universe's expansion becomes infinitely fast. Current data suggests this extreme fate is unlikely, since dark energy seems constant in its effect, but we can't be entirely sure. Conversely, it's not impossible that dark energy could one day switch off or change behavior. After all, we don't know what it is. If it were to diminish or reverse, gravity could take over again, potentially leading to a slow halt of expansion, followed by a big crunch where everything converges again. Some speculative ideas even suggest a big crunch could rebound into a new Big Bang, a cyclic universe. But all evidence right now indicates our universe is on the infinite expansion track. Thinking about these cosmic futures can be unsettling. The time and scales involved are beyond comprehension, and the idea that all we see will eventually fade can feel bleak. Yet, there's another way to see it. We live in the universe's splendid youth. Stars are abundant, galaxies gleam, life is possible because energy differences exist and suns shine. We are, by sheer cosmic luck, here at a time when we can witness other galaxies. In the far future, cosmic expansion will hide them from view. And when our own galaxy still has the raw material to birth new stars. In a sense, this is the heyday of the cosmos, or one of its heydays. And it will last a long time yet. Trillions of years of starlight are still to come before the long twilight. Perhaps by then, if there are distant descendants of humanity or entirely other life forms, they will have figured out ways to survive and find meaning, even as the universe's lights go out. Or they might traverse to other universes if such a thing is possible. These far futures give perspective. They show us that even stars and galaxies have life cycles, and that change is the only constant, even on the grandest scales. Contemplating the multiverse, the quantum origins of existence, and the far destiny of all things can make our everyday concerns seem small. Our lives, and even our entire species, are brief flashes in the cosmic timeline. And yet, the fact that we can contemplate these grand questions gives our brief flashes a kind of significance that isn't measured in time or size. We are part of this universe, literally made of its atoms, forged in stars, and through us, the universe has gained the ability to reflect on itself. We often quote the line that we are stardust. Equally, we are the universe's way of thinking and feeling, at least in this corner of it. These theoretical frontiers are challenging and sometimes disorienting, but they also inspire a deep sense of wonder. They remind us that there is so much we don't know, and that the quest for understanding is far from over. They also have practical philosophical effects. For instance, knowing the likely fate of heat death gives a certain poignancy to all we do, like ephemeral art that you know won't last, but is beautiful in the moment. It emphasizes that meaning isn't necessarily in eternality, but in experience and knowledge itself. The multiverse idea on the other hand, can be oddly comforting or humbling. It suggests that our universe might not be the only way things could be, that perhaps somewhere every possibility exists. While that might make us feel small, one universe among who knows how many, it also suggests that existence as a whole is rich and exuberant beyond imagining. Amid these cosmic scales and abstractions, one thing remains tangible and immediate. Us, here, now. We find ourselves on a small planet, in a vast universe possibly filled with other universes. And what do? We explore. We reach out. We plan, and we dream. The theoretical frontiers we've explored in thought push us toward an inevitable reflection on our own journey and destiny as humans. We've learned that the universe won't cater to us. It's we who must adapt and venture if we want to endure and matter. And so we turn to the next chapter of our exploration, the saga of human space travel and the future we imagine among the stars. For as long as we've gazed up at the sky, we humans have felt the pull to journey outward. Our ancient ancestors looked at the moon and planets and spun stories about gods and realms in the sky. But it was only in the last century that we devised the means to actually go there. In a stunningly short period, just about 6 decades, we went from the first powered airplane flight to leaving footprints on the moon. The Apollo 11 moon landing in 1969 was a pinnacle of that early space age. When Neil Armstrong climbed down the ladder and set foot on the lunar surface, it was indeed a small step for a man, but symbolically a giant leap for mankind. In that moment, humanity became a multi-world species, if only for a brief visit. The image of an astronaut bouncing in 1/6 gravity, leaving boot prints in the grey dust, with our dazzling blue Earth hanging in the sky above him, is etched into our collective memory. It gave us a new perspective. We saw our world from the outside, small and fragile, and we saw ourselves capable of doing the seemingly impossible. After the moon landings, human exploration paused on interplanetary travel, but not on venturing beyond our atmosphere. We built space shuttles and space stations, learning how to live and work in orbit for months on end. The International Space Station, ISS, which has been continuously occupied by rotating crews since the year 2000, is a triumph of international cooperation. Astronauts from many nations have lived side by side in that research outpost, conducting science in microgravity and learning how space affects the human body. Every day on the ISS, crews witness 16 sunrises and sunsets. They float in a laboratory that circles Earth at 28,000 kilometers per hour, sometimes looking down at night to see the lights of cities and thunderstorms flickering, and sometimes looking out into deep space with the sun's glare blocked to reveal a sky thick with stars. The ISS taught us how to recycle air and water, how to maintain machines in space over long periods, and how to handle emergencies far from immediate help. Just as importantly, it taught us that when you see Earth from that vantage, a glowing blue marble against black, borders seem pointless and petty. Many astronauts return profoundly moved, carrying what's called the overview effect, a shift in consciousness, recognizing the unity and fragility of our home planet. This experience has been recounted again and again. Seeing Earth as one whole makes one keenly aware of how interconnected we all are and how delicate the balance of life is. Now, half a century after Apollo, there is a new surge of momentum to go beyond Earth orbit again. The Moon, our closest neighbour, calls us back, this time not just to visit, but to stay. NASA's Artemis program, named after Apollo's twin sister, envisions sending astronauts, including the first women, to the lunar South Pole in the coming years. Why the South Pole? Because in craters there, untouched by sunlight for eons, lies water ice. Water can be split into hydrogen and oxygen, vital components for fuel and breathable air. If we can harvest lunar ice, the moon could serve as a refueling depot and a base camp for further exploration. Plans are underway to build a lunar outpost, perhaps a small habitat module initially, with power systems and rovers, where crews can spend weeks or months. We will learn to use the moon's resources, to live off the land, in a sense. The challenges are many. Astronauts will face long, cold lunar nights, 2 weeks long, unless habitats are built near light-rich peaks, and they'll have to contend with pervasive lunar dust and higher radiation than on Earth. But solving these problems will teach us how to operate independently of Earth's constant support. The moon will also be a testing ground for the next big leap. Mars. Often called the ultimate destination for early human exploration, Mars has loomed in our dreams for decades. It's the most Earth-like planet after our own. It has a day just 40 minutes longer than Earth's, seasons, polar ice caps, and a variety of surface features like dry river valleys, canyons, and volcanoes. Yet, it's far from welcoming. The air is mostly carbon dioxide and extremely thin, about 1% of Earth's atmospheric pressure. The weather can be harsh, dust storms that engulf the whole planet, and temperatures that can plunge far below freezing. Still, Mars is the only other planet in the solar system where humans could, with a lot of preparation, potentially live and work long-term on the surface. Getting there is a monumental challenge, roughly 6 to 9 months in deep space one way, and you can only launch when Earth and Mars are properly aligned, about every 26 months. That means any Mars mission is a commitment of years, not months. The distance means that, unlike the Apollo days when astronauts spoke with mission control in almost real time, Mars explorers will often face up to 20-minute delays in communication each way, necessitating far more autonomy. Despite these challenges, numerous mission plans have been drawn up. They typically involve pre-sending supplies and equipment to Mars that land before the crew, so when humans arrive, there are habitats, or at least components, waiting. Astronauts would likely live in a habitat, maybe inflatable or made from Martian soil bricks, and use pressurized rovers to explore long distances. One key is to make use of Martian resources. For example, Mars has abundant carbon dioxide in the atmosphere and water ice in the ground. Using relatively simple chemistry, we can combine CO2 and hydrogen from water to make methane fuel and oxygen. This is called in situ resource utilization. NASA has even sent an experiment called MOXIE on the Perseverance rover to test producing oxygen from Martian CO2, a small but crucial proof of concept. Standing on Mars will be surreal. The sky is butterscotch-coloured during the day because of fine dust. The sun is about half the size it appears from Earth, and on occasion you might see Earth as a tiny bluish star in the dawn or dusk sky. Future astronauts will contend with 38% Earth gravity, so they'll feel much lighter, and they'll have to wear suits whenever they step outside their habitat. But they might also get to witness marvels up close that we've so far only seen through rover cameras: the towering Mount Olympus, tallest volcano in the solar system, the grandeur of Valles Marineris, a canyon system that would span the width of the United States, or simply the strange beauty of a Martian sunset, where the sky turns a bluish hue near the sun as it dips below the horizon. The timeline for Mars is not set in stone, but many in the space community hope for the first human mission, sometime in the 2030s or 2040s. There is fervent effort from both national agencies and private companies to develop the heavy lift rockets, spacecraft, and life support systems that would make it possible. A new generation of giant rockets, like NASA's Space Launch System and SpaceX's Starship, are being built to carry large cargoes into space and possibly to the Moon and Mars. If Apollo was the sprint, what comes now is more of a marathon, establishing sustainable exploration. Yet Mars is not the end goal for human imagination. It's just the next tangible one. People dream of bases on the moons of Jupiter or Saturn, or even floating cities in the clouds of Venus, where about 50 kilometers up, temperatures and pressures are surprisingly Earth-like, even though everything else about Venus is hellish. We talk of mining asteroids for materials, of placing habitats at stable points in space called Lagrange points, and of building great rotating space colonies, as some visionaries like Gerard O'Neill imagined in the 1970s, enormous cylindrical habitats with farmland and towns inside, spinning to create artificial gravity. While those concepts remain theoretical for now, they spark discussions about the far future. Could humanity actually expand into the solar system in a substantial way? If we think centuries ahead, not just decades, might there be millions of people living off Earth? The idea of colonization beyond Earth raises big questions. Technical ones, like how to grow food in alien soil, or how to shield colonists from cosmic rays over a lifetime. And also, ethical and philosophical ones. When we say colonize, our history on Earth reminds us that colonization often had a dark side. We won't find native peoples on Mars to displace, but there could be native life, say, bacteria beneath the surface. What obligation do we have to avoid harming an ecosystem on Mars if it exists? Should Mars, or parts of it, be declared a scientific preserve? We will need to grapple with planetary protection versus the drive to settle. Moreover, as humans live away from Earth, how will our culture change? People born on Mars might eventually see themselves as Martians, distinct from Earthlings. Will there be new dialects, new customs? If one day there are children who have never known Earth except as a point of light, their perspective on the universe will be unique in human history. Practical challenges abound as well. Building a colony is not just dropping people on a planet and waving goodbye. It means establishing a closed-loop life support system where air, water, and nutrients are recycled almost perfectly, because resupply from Earth will be very limited. It means generating energy, likely solar or nuclear power, and storing it for the long Martian nights or lunar nights. It means developing medicine and emergency procedures when Earth hospitals are too far away. All these are being studied right now. Scientists are growing plants in Mars-like soil simulants. Engineers are testing 3D printing habitats using moon dust analogues. Doctors are studying health effects of partial gravity by simulating it. Bit by bit, the technologies needed for off-world living are being developed. While NASA and other agencies provide much of the effort, the rise of private space companies has truly changed the landscape. Companies are not just launching satellites anymore. They're ferrying astronauts to the ISS and planning private missions to the moon and beyond. This commercial involvement could reduce costs and spur innovation through competition. One company envisions 1,000 large spacecraft taking settlers to Mars in coming decades. Others are planning inflatable space habitats that could serve as orbiting hotels or research labs. We are seeing the start of a space economy beyond just government contracts, perhaps mining asteroids for rare metals, or lunar tourism, or even manufacturing in microgravity. It's an exciting and somewhat unpredictable era, reminiscent of the early days of aviation, when many players were trying different designs. Humanity's cosmic odyssey, however, isn't just about the physical act of spreading out. It's also about what it means for us as a species. Why do we go? The reasons are as varied as human aspirations. Part of it is the classic explorer's ethos, because it's there, as mountaineer George Mallory said about Everest. We go because we're curious, because we want to see what's on the other side of the hill, or the planet. Another part is survival and long-term thinking. to not have all our eggs in one basket. A single planet species is vulnerable to extinction from planet-wide catastrophes, be it self-inflicted or natural, like giant impacts. If humans live on multiple worlds, our chances of survival as a species increase. There is also the drive for progress and prosperity. New frontiers often spur innovation, provide resources, and inspire generations. But beyond these practical and almost instinctual reasons, there's a philosophical one: perspective. When we venture into space, we see ourselves from a new vantage point. The astronauts often talk about how trivial differences seem when you're looking at Earth as one whole. Our cosmic odyssey may ultimately make us more mature as a civilization, uniting us with a common identity as citizens of Earth, and eventually, perhaps, as citizens of the solar system. By seeing Earth as just one world among many, we might finally break the illusion that our particular nations or cultures are the center of the universe. We carry our conflicts and biases with us, sure, but space has a way of underscoring our commonality. The pale blue dot photo, taken by Voyager 1 as it left the solar system, showed Earth as a tiny speck in a sunbeam. Carl Sagan eloquently reminded us how, on that dot is everyone you love, everyone you know, everyone you ever heard of, every human being who ever was. The more we travel, and perhaps settle away from Earth, the more real that understanding becomes. Consider how an early Martian settler might feel looking up at Earth in their sky. To them, Earth would be a beacon of warmth and colour, a place they might long for if they were born on Mars and only heard of its blue oceans and green forests in stories. In that sense, going outward may renew our appreciation for what we have here. It might also force us to take better care of Earth, knowing how hard it is to make other places livable. Earth is, after all, the absolute paradise for us, and every other place is extremely hostile by comparison. The effort required to keep a handful of people alive on Mars for a week is tremendous. It really drives home how wonderfully self-sustaining Earth has been for billions of years. That recognition can fuel a stronger environmental ethic. As we cast our eyes to the stars, we should also remember to cherish the soil under our feet. The voyages of Apollo to the Moon brought about an unintended but powerful consequence. The environmental movement got a boost. Seeing Earth from space in its entirety made many realize its fragility. Now, as we plan for longer and more permanent journeys, this awareness only grows. Perhaps when humans live on the sterile Moon or the barren Mars, they will be the greatest environmentalists for Earth, advocating to preserve the vibrancy of the only garden we know. They will also bring a bit of Earth with them. Every closed habitat with a greenhouse or every batch of seeds taken to start a farm on Mars is like a little piece of Earth transplanted. In that way, we extend Earth's reach, spreading not just humanity, but Earth life, a prospect some find poetic and others urge caution about, to avoid contaminating possible alien ecologies. Looking further down the road, if we succeed in planting sustainable colonies on the Moon, Mars, and perhaps other places, the next dream is interstellar travel, journeys to planets around other stars. That remains the province of the very distant future. The stars are staggeringly far away. The fastest spacecraft we have launched, Voyager, New Horizons, would take tens of thousands of years to reach even the nearest star at their current speeds. So to travel there in any reasonable time, we'll need breakthroughs, maybe fusion propulsion, antimatter engines, or concepts like light sails pushed by powerful lasers. One such concept, Breakthrough Starshot, envisions sending gram-sized probes to Alpha Centauri that way, reaching it in 20-30 years. For human travel, even more exotic ideas like warp drives or suspended animation are often discussed in theory, but nothing concrete exists yet. Still, history has shown that what is impossible in one century can become merely difficult in the next, and routine in the one after that. If one imagines humanity, or our evolved or AI descendants, surviving for thousands or millions of years, it's hard to believe we would never attempt to bridge the interstellar gulf. There are whole other solar systems out there, hundreds of billions in our galaxy alone. We might be content in our solar system for a very long time, but eventually, the same curiosity that took us across oceans, then into space, may push us out beyond the Oort cloud, the distant comet reservoir at the fringe of our solar system, toward another sun's warm glow. It's a daunting challenge, of course. One can imagine generation ships, huge self-contained worldlets that travel for centuries, with successive generations living and dying aboard before reaching a new star. Or perhaps advanced propulsion could cut travel to a few decades, allowing the same crew to start on Earth and finish at the destination. These are speculative scenarios, but they remind us that impossible is often just a matter of technological development and time. They also raise deep questions about who we will be by then. Will our species diversify, biologically or culturally, once spread over multiple planets? Perhaps one day, humans scattered on different worlds will drift apart, not just physically, but in values or even form, the way species diverge when separated. Or maybe the connectivity, through communications technology, will keep a common thread of humanity tying us together, a shared heritage and purpose. These are questions for future philosophers and leaders. Right now, we are at the dawn of this odyssey. We stand with rocket engines firing beneath us and hope pushing us forward. We are like sailors embarking from a familiar shore into a vast, uncharted ocean. We carry with us not only our ambition, but also our frailties and wisdom. One hopes in good measure. Space will test us in every way: our ingenuity, our cooperation, our perseverance. The vacuum of space does not compromise. The laws of physics are strict. To live beyond Earth, we'll have to be our best, precise, innovative, and unified. In that way, space exploration is a mirror that forces us to confront both our limitations and our potential greatness. As our journey into space progresses, we find ourselves often pausing simply to marvel at what we are doing. A little over a century ago, human flight itself was novel. Now, a human presence exists continuously, 400 kilometers above Earth, and machines built by us roam the surfaces of Mars and the Moon, and have even left the solar system entirely. Voyager 1 and 2 are now interstellar ambassadors, carrying golden records with sounds and pictures of Earth. The boundary between what is science fiction and science fact keeps shifting. We live in a time when the far side of the Moon has been seen, when rovers take selfies on Mars, and when a single spacecraft has visited all classical planets, thanks to Voyager and others. And soon, perhaps, we'll live in a time when people are working on the Moon again and planning their next stop on Mars. In considering the saga of human exploration, it's striking that it reflects a fundamental truth. We began as wanderers, and we are wanderers still. Our ancestors migrated across Earth, and now Earth itself is not enough to contain our wanderlust. This drive might very well be an evolutionary advantage. It makes us spread out, so we're not all wiped out by one local calamity, and it makes us resourceful. Or it might just be a neutral quirk of our psychology that happens to carry us far. Either way, it defines us. The act of exploration, of stepping into the unknown, is one of the noblest enterprises we undertake. It's inherently risky, and often costs much, but it rewards us with knowledge, with inspiration, with a renewed spirit. Now, after reflecting on our tools and journeys, our searches and theories, our hopes and plans, we find ourselves at a juncture. It's time to take a step back and absorb the panorama of what all these endeavours mean. We have peered into the atom and out to the cosmic horizon. We have walked on the moon and mapped the genome. We have found planets around other stars and measured the universe's age. We have, in a sense, been assembling a grand mosaic of understanding. Each piece might seem separate, one dealing with telescopes, another with rovers, another with equations of spacetime, but they are all part of a single human story, the story of our expanding comprehension and presence in the cosmos. Night falls, and above us spreads the infinite sky, a tapestry of stars, galaxies, and possibilities without end. As we conclude this long journey of exploration and discovery, we remain, in many ways, at the beginning. The more we learn, the more we realize how much remains unknown. We still stand under that night sky much like our ancestors, awed by its splendor and mystery, even if we now understand a bit of what we see. Each discovery we've recounted, each new window opened by a telescope, each footprint on an alien world, each puzzling signal from the depths of space, each elegant theory, has not closed the book on wonder, but opened new chapters. For every question we've answered, a dozen new ones have sprung up. This is the eternal cycle of knowledge, and that is the enduring beauty of the cosmos. It is inexhaustible. Our capacity for wonder is met with an endless supply of wonders. We could explore for 1,000 years and hardly scratch the surface of what's out there. This might seem daunting, so much unknown, but it's also comforting in a way. It means we will never run out of new horizons to chase, new phenomena to investigate, new beauty to encounter. The sky's infinity guarantees that the voyage of discovery will go on forever. Generations not yet born will have their own astounding findings, their own daring adventures among the stars. Imagine, for a final moment, a lone figure stargazing on a clear night. Perhaps it's you, or a child in some future colony, looking up at an unfamiliar sky. Above, countless stars shine, some perhaps with faint tint of colour, others pulsing gently. The Milky Way arcs overhead as a hazy band. In that moment, whether on Earth or on some distant moon, that person feels simultaneously tiny and connected to something vast. The infinite sky has a way of humbling us, reminding us that we are small in size, yet we are also part of all this immensity. Our atoms were born in stars. Our destinies are tied to the cosmos. That awareness, passed from generation to generation, is one of the greatest gifts of astronomy and space exploration. As long as humans exist, we will likely continue to look up in wonder. We will continue to ask big questions. Are we alone? How did it all begin? What's out there, beyond the next hill, the next planet, the next galaxy? These questions define us as much as our answers do. Perhaps in the far future, our descendants, maybe evolved, maybe cyborg, maybe a species or AI we can't even imagine, will have gathered encyclopedias of knowledge about the universe. Perhaps they will have neighbours from other stars, or recolonized what was once Earth, if we've had stumbles. It could be that by then, the idea of the unknown will have shifted to scales, or realms we currently can't conceive. But even then, we can bet they will have their own frontier to explore. There may be other dimensions, or the engineering of universes, or diving into the deepest layers of reality. The pursuit of knowledge and experience is likely endless, and that is as it should be. We shall not cease from exploration, and the end of all our exploring, as a poet said, will be to arrive where we started and know the place for the first time. In exploring the universe, we have come to view our own world with new eyes. By climbing the mountain of knowledge, we attained a clearer view of the valley of our everyday existence. We returned from the moon and noticed Earth's atmosphere needed care. We detected other planets and realized how special a biosphere is. We studied the stars, and in doing so, learned the chemistry of our own bodies. In exploring outward, we have also journeyed inward. We have discovered things about our own nature, our resilience. Keeping astronauts alive in space for a year tests that. Our ingenuity, every rover landing, every ingenious gravity assist trajectory, and our tendency to unity or conflict under pressure. Space exploration has seen both cooperation, international crews working in harmony, and competition, the early space race. It has brought out some of the best in us: valor, sacrifice, intellect, creativity. It also mirrors our societal choices. Do we fight over resources or pool them for a common goal? So far, it's been a mix, but there's hope that the further we go, the more we'll see the wisdom in going together. Now, as this narration draws to a gentle close, we feel a sense of calm reverence for all that we've considered. The cosmos is vast beyond imagination, yet we have the privilege of being part of it and of comprehending some of its laws. We've unleashed our robotic emissaries across the solar system and extended our senses to the edge of time. We've begun to step physically into the void, carefully, but with determination. We have a long, long way to go, but looking back at how far we've come, we can't help but be quietly proud and hopeful. The sky above remains infinite and inviting. Generations past gazed up and created constellations and myths. We gaze up and see galaxies and future journeys. Generations to come will gaze up and perhaps see new colours in the sky, the lights of settlements, or the glint of distant spacecraft heading outward. Under that infinite sky, all of us, past, present, future, share a common wonder. We close this chapter of our cosmic story with a sense of completion, yet not finality. It is a completion of a thought, of a moment in time, but the story itself goes on, as endless as the stars. The universe continues to unfold its secrets, and we will continue seeking them. Each day, new data arrives. Each year, new theories are born or validated. Each decade, new destinations are reached. The journey truly has no end, but that is not cause for sadness. It means there will always be something to strive for, always room to grow. The cosmos, in all its enormity, is patient and awaiting our curiosity. It has no urgency, but we do. The brief flicker of our lives impels us to seize the opportunity to learn and explore while we can. And as we do, we contribute our verse to the grand poem of existence. So, beneath the silent stars and the glowing band of the Milky Way, we take a deep breath and feel at peace. We feel connected to the first astronomers who ever wondered, and to the last explorers
who will ever roam among the galaxies. We find meaning in the very act of searching and understanding.
The night might be cold and dark, but we carry within us the warmth of knowledge and the light of curiosity, our torches against the darkness. The journey continues, quietly and relentlessly. From new telescopes switching on and peering at their first starlight, to new rockets roaring upward, carrying dreams, to equations being scribbled on chalkboards that might describe the fabric of reality, the quest goes on. As we end our narrative here, somewhere a child is looking up at the sky, perhaps seeing the moons of Jupiter through a telescope for the first time, or marveling at a shooting star. That sense of wonder will spark new questions, new investigations. And thus the baton passes on. In the grand theatre of the cosmos, we have now taken our seats as active participants, not just passive spectators. We have begun to reveal the cosmos, and in turn, it has revealed us to ourselves. Let us continue this voyage with humility, curiosity, and care. Our story is but a tiny part of the universe, but it is a precious one, to us at least. And as long as we continue to explore, to learn, and to reach outward and inward, our story will remain a worthy part of the cosmic tapestry. Under the infinite sky, with stars above and earth below, with the past at our back and the future unrolling before us, we conclude this chapter of discovery. The cosmos is there, waiting, and we, its children, will keep journeying onward. The adventure of exploration lives on, carried by all those who look up and feel the call of the unknown. In that sense, this ending is only the beginning of what comes next. Safe travels, fellow explorers. The universe awaits.